Everything around us, from the twinkling stars high above to the solid ground beneath our feet, is made up of a tiny yet incredibly powerful force, the atom. These minuscule building blocks form the very foundation of existence. But what exactly are atoms, and how did they come to be the universal unit that shapes everything in the universe? Join us as we take a deep dive into the enigmatic world of atoms, unveiling their true nature, their historical evolution, and their mysterious role in the grand cosmic design. At its core, an atom is the fundamental unit of matter. It is the basic building block from which everything in the universe is formed. Each atom is a complex structure made up of three main subatomic particles: protons, neutrons, and electrons. These components play specific roles in determining the atom's identity and behavior. At the very heart of the atom lies the nucleus, where protons and neutrons are packed together. Surrounding this nucleus are the electrons, which orbit in defined shells at varying distances from the center. Protons are positively charged particles, and the number of protons in an atom defines the type of element it is. This number is referred to as the atomic number. For instance, hydrogen, the simplest of all elements, has just one proton in its nucleus, while carbon contains 6. Neutrons, on the other hand, have no charge at all and are essential in contributing to the overall mass of the atom. The number of neutrons can vary even within atoms of the same element, leading to different isotopes. Electrons are far smaller than protons or neutrons and carry a negative charge. They orbit the nucleus in distinct energy levels. These electrons are responsible for the chemical properties of an atom, as their arrangement in the atom's electron shells dictates how the atom will interact with others. The behavior of these electrons plays a crucial role in forming chemical bonds between atoms, which in turn creates the vast array of molecules and compounds that make up the world around us. Understanding atomic structure is essential not only in chemistry and physics, but also in unraveling the deeper mysteries of the universe. The atomic framework governs not just the material world we experience every day, but also the intricate interactions that occur on the farthest reaches of the cosmos. At the most basic level, the forces that hold atoms together are governed by the fundamental interactions of physics, and these interactions form the bedrock of all matter. The key players within the atom are the subatomic particles: protons, neutrons, and electrons. Protons, with their positive charge, reside at the heart of the atom, while neutrons, being electrically neutral, help balance out the atom's mass. Both particles are tightly bound in the nucleus by the strong nuclear force, one of the 4 fundamental forces that govern the universe. This force operates over incredibly short distances, and without it, protons and neutrons would fly apart due to the repulsion between like charges. Electrons, on the other hand, are held in their orbitals by the electromagnetic force, which draws them toward the positively charged nucleus. However, the electrons remain in defined energy levels, preventing them from spiraling into the nucleus. This delicate balance between the attractive forces of the protons and the repulsive forces of other electrons ensures the stability of the atom. Interestingly, it's the configuration of electrons in their outermost shells that determines how an atom will interact with others. These outer electrons, known as valence electrons, play a crucial role in the atom's chemical reactivity. Atoms seek stability, often by sharing, gaining, or losing electrons in a bid to achieve a full outer shell. This process leads to the formation of molecules, compounds, and the incredibly diverse array of materials we encounter in our daily lives. The interactions of these subatomic particles not only define the characteristics of individual atoms, but also shape the behavior of all matter in the universe. The way atoms bond and react with each other under varying conditions explains the vast variety of substances, from the simplest gases to the most complex biological molecules. By understanding these interactions, we unlock the fundamental workings of the universe. Zooming in even further, we come to quarks, the fundamental particles that make up protons and neutrons, which are the building blocks of atomic nuclei. Every proton and neutron is made of 3 quarks, tightly bound together by the strong nuclear force. These quarks are held in place by force-carrying particles known as gluons, which act like glue, ensuring the quarks remain bound within the protons and neutrons. Each quark carries a fractional electric charge. The up quark has a charge of 2/3, while the down quark carries a charge of -1/3. This specific combination of quarks within protons and neutrons results in the proton's positive charge and the neutron's neutrality. The fascinating thing is that most of the mass of protons and neutrons doesn't actually come from the quarks themselves, but rather from the energy associated with the strong force that binds them together. This relationship between mass and energy is described by Einstein's famous equation, EmC². The gluons that mediate the strong nuclear force are massless particles, but they contribute significantly to the overall mass of atomic particles through their interactions with quarks. Understanding quarks and their role in the structure of protons and neutrons helps us get closer to understanding the very nature of matter itself. As the building blocks of atomic nuclei, quarks shape the way atoms behave, influencing everything from the chemical bonds they form to the physical properties that govern the universe. By studying these tiny particles and their interactions, scientists are continually unlocking the mysteries of the cosmos at its most fundamental level. The more we understand quarks, gluons, protons, neutrons, and electrons, the closer we come to understanding the deeper forces that shape the universe. Each discovery brings us one step closer to uncovering the ultimate secrets of existence. Every element on the periodic table is defined by its atomic structure. The nucleus of each atom consists of protons and neutrons, while electrons orbit the nucleus in shells or energy levels. The number of protons, known as the atomic number, is what determines the identity of the element. For example, hydrogen with 1 proton is the simplest element, while carbon, with 6 protons, is the basis of life as we know it. Electrons with their negative charge orbit around the nucleus in a specific pattern, influencing the atom's chemical properties and reactivity. Elements are grouped together based on similarities in their electron configurations. The noble gases, alkali metals, and halogens each exhibit unique behaviors due to the arrangement of electrons in their outermost shells. As we move across the periodic table, the number of protons in the nucleus increases, which in turn increases the positive charge of the nucleus. This greater positive charge pulls electrons closer to the nucleus, changing their energy levels and affecting the atom's overall behavior. As we move down a group on the periodic table, the size of the atom increases, and the outer electrons are further from the nucleus. This makes metals more reactive as the outer electrons are more easily lost. Conversely, nonmetals tend to become less reactive as we move down the groups due to the increased distance between the outer electrons and the nucleus. In the end, the arrangement of atoms from their atomic structure to the forces that bind them together is what shapes the universe. From the tiniest quark to the vast cosmic structures, the interactions between atoms and subatomic particles govern everything that exists. Atomic structures are not as simple as they might initially appear. They are intricate, complex systems with variations that lead to vast differences in behavior and properties. One significant variation lies within the concept of isotopes, atoms of the same element but with different numbers of neutrons. This subtle change plays a crucial role in how atoms behave. It affects everything from the atom's stability to its interaction with other elements, its density, and how it reacts in nuclear processes. By studying these isotopes and atomic structures, scientists can unlock the mysteries of why elements behave the way they do during chemical reactions and natural cycles, ultimately revealing the complexity of the material world that surrounds us. As we explore atomic structure, we encounter a critical development, the electron cloud model. This revolutionary concept drastically changed our understanding of atomic behavior. Before this model, the Bohr model reigned supreme. Bohr suggested that electrons orbited the nucleus in fixed, definite paths or orbits. However, the electron cloud model introduced a much more nuanced and dynamic vision of the atom. It depicted electrons not as particles fixed in one place, but as existing in probabilistic clouds surrounding the nucleus in regions defined by quantum mechanics. This idea, rooted in quantum theory, was groundbreaking. Instead of envisioning electrons as orbiting like planets around the sun, the cloud model saw them as existing in uncertain locations, defined by probability. Rather than a rigid path, the location of an electron at any given time is a matter of probability, represented by the density of the cloud. Areas with denser clouds are more likely to contain an electron. This realization that electrons don't have fixed locations but instead exist within probabilities is a cornerstone of quantum mechanics, which holds that particles, like electrons, have both wave-like and particle-like properties. This shift in perspective has far-reaching consequences. It fundamentally altered how we understand atomic behavior. By acknowledging this uncertainty, scientists can more accurately predict the behavior of atoms in various contexts. The electron cloud model is essential for explaining chemical bonding. It is through the arrangement and behavior of electrons that atoms can bond with one another to form molecules, and the nature of these bonds dictates much of the physical and chemical properties of substances. For example, whether atoms form ionic, covalent, or metallic bonds depends on the behavior of the electrons in the outermost shell of each atom. The cloud model helps us comprehend how and why these bonds form, allowing scientists to manipulate reactions with precision in fields ranging from materials science to medicine. In short, the electron cloud model has been instrumental in advancing our understanding of atomic interactions. It offers insight into the structure of atoms, how they bond, and how they interact in complex chemical reactions. The model has propelled advancements in various fields, including electronics, where it helps explain the behavior of semiconductors, and in the pharmaceutical industry, where it aids in drug design. As we continue to study atomic interactions at increasingly detailed levels, the electron cloud model remains a fundamental tool guiding our exploration of the universe at its most fundamental scale. The development of atomic theory is a fascinating journey, one that has been shaped by the contributions of brilliant minds across centuries. In fact, this journey began long before modern science, with the ancient Greeks. The philosopher Democritus, around 450 BCE, was one of the earliest to propose the idea that everything in the universe is composed of tiny, indivisible particles called atomos, meaning uncuttable. While his ideas were philosophical and lacked experimental proof, they sparked a crucial line of inquiry into the nature of matter itself. Although Democritus' theories were far ahead of their time, they set the stage for the scientific pursuit of understanding atoms. Fast forward to the 19th century, when John Dalton reintroduced the idea of atoms based on experimental evidence. Dalton's atomic theory posited that all elements are made of atoms, and that atoms of a given element are identical in weight and properties. This marked a significant departure from earlier theories and laid the groundwork for the development of modern chemistry. His theory was based on a systematic approach, emphasizing that chemical reactions occur through the rearrangement of atoms, forming compounds. Dalton's work, though rudimentary by today's standards, provided a strong foundation for future discoveries. The late 19th century saw another leap forward thanks to J.J. Thomson. Through his experiments with cathode rays, Thomson demonstrated that atoms were not indivisible, as once believed. In his groundbreaking discovery, he identified the electron, a tiny, negatively charged particle within the atom. This discovery shattered the long-held notion that atoms were indivisible and unchanging. Thomson proposed the plum pudding model of the atom, suggesting that electrons were embedded within a positively charged soup. This idea, though later disproven, was crucial in advancing our understanding of atomic structure and opening the door for future theories. Then came Ernest Rutherford, whose gold foil experiment in 1909 changed everything. Rutherford discovered that atoms are mostly empty space, with a small, dense nucleus at their center. The nucleus, he found, contained positively charged protons and neutrally charged neutrons, while electrons orbited this nucleus. This discovery led to the nuclear model of the atom, which describes the atom as having a central nucleus surrounded by electrons. Rutherford's work revolutionized the field and set the stage for the quantum mechanical models that would follow. The work of these pioneering scientists was a series of progressive breakthroughs that gradually revealed the atom's true nature. Their collective contributions marked a significant evolution in our understanding of matter and its behavior. With each new discovery, the picture of the atom became clearer, and our ability to manipulate it grew exponentially. These advancements paved the way for the development of quantum mechanics and the eventual discovery of the electron cloud model. At its core, The study of atomic theory represents a journey of human curiosity and perseverance. What began with the ancient Greeks' philosophical musings on the nature of matter has evolved into a sophisticated understanding that continues to shape the scientific world today. From Democritus to Rutherford, and from Bohr to quantum mechanics, each step in the development of atomic theory has revealed new layers of complexity about the universe we inhabit. And as we continue to explore the smallest scales of matter, we can only imagine the new revelations that await us in the world of the atom. However, despite its intriguing potential, there was no empirical evidence to support the atomic theory in its early stages. As a result, the idea faded into obscurity. During the long reign of Aristotelian philosophy, which dominated Western thought for centuries, the focus shifted toward a more qualitative understanding of the natural world. Theories about matter were rooted in the belief that everything was composed of four fundamental elements: earth, water, air, and fire. This conceptualization of the world was not one based on empirical observation, but rather on philosophical and speculative thought. It wasn't until the 17th century, when the foundations of the scientific method began to take shape, that the notion of the atom saw a resurgence. Visionary scientists such as Robert Boyle and John Dalton revived interest in the atomic theory, albeit through a more rigorous, experimental lens. Boyle's work laid the groundwork for a new, evidence-based approach to chemistry, emphasizing observation and experimentation over philosophical speculation. Dalton, in particular, in the early 19th century, formulated the first modern atomic theory. His groundbreaking work concluded that elements are composed of indivisible particles called atoms, which remain unchanged during chemical reactions. He also proposed that atoms of different elements differ in their weights and properties, a realization that paved the way for future atomic models. Dalton's atomic theory was instrumental in establishing the idea that atoms form the very foundation of chemical reactions. This early model of the atom, however, was limited in scope and lacked the sophistication that would emerge in subsequent years. As research into the nature of matter advanced, new discoveries led scientists to refine and expand their understanding of atomic structure. One of the most notable contributions to atomic theory came from J.J. Thomson, who in the late 19th century conducted pioneering experiments with cathode rays. His work led to the discovery of the electron, a fundamental subatomic particle. To explain this finding, Thomson proposed the plum pudding model of the atom, where electrons were thought to be embedded in a positively charged soup or cloud. This model was revolutionary for its time, though it would eventually be supplanted by new insights that emerged in the early 20th century. At the dawn of the 20th century, a series of groundbreaking experiments dramatically altered our understanding of the atom. One of the most significant developments occurred in 1912, when Ernest Rutherford conducted his famous gold foil experiment. Rutherford directed a stream of positively charged alpha particles at a thin sheet of gold foil, expecting the particles to pass straight through, given the prevailing model of the atom. Instead, to the astonishment of the scientific community, a small fraction of the particles were deflected at large angles, and some even bounced back. This unexpected result suggested that atoms are mostly empty space, with a tiny dense nucleus at the center containing most of the atom's mass. Rutherford's findings forced a complete re-evaluation of the atomic model, shifting the focus from a diffuse, uniform structure to one with a compact, centrally located nucleus. Following Rutherford's breakthrough, the atomic model was further refined by Niels Bohr, who introduced the idea of electron orbits. Before Bohr's work, the arrangement of electrons within an atom was still speculative. Bohr proposed that electrons travel in defined orbits around the nucleus, much like planets orbiting the sun. This model was instrumental in explaining the hydrogen atom's emission spectrum, as it accounted for how electrons could absorb and release energy when transitioning between orbits. By incorporating quantum principles, Bohr's model marked a pivotal moment in atomic theory. It expanded our understanding of atomic structure and helped lay the groundwork for the quantum mechanical approach that would emerge in the coming decades. As the 20th century progressed, more discoveries further reshaped our view of the atom. In 1932, James Chadwick conducted experiments that revealed the existence of neutrons within the atomic nucleus. Chadwick's discovery was crucial in refining the atomic model, as it demonstrated that the nucleus is not only composed of positively charged protons, but also neutrally charged neutrons. The neutron contributed to the atomic mass without affecting the atom's overall charge. This revelation had profound implications, particularly in the understanding of isotopes, atoms of the same element that have different numbers of neutrons. Isotopes exhibit nearly identical chemical properties, but may differ in physical properties such as mass and stability. In the early 20th century, the development of quantum mechanics brought about a fundamental shift in the way we conceptualize atomic behavior. Experiments in electron diffraction and the study of atomic spectra revealed that electrons cannot be thought of as particles following fixed paths, as Bohr had originally proposed. Instead, electrons behave as wave functions that are spread out across space. This realization led to the development of the modern quantum mechanical model of the atom, which describes the behavior of electrons in terms of probabilities rather than certainties. According to this model, it is impossible to precisely predict the position of an electron at any given moment, but it is possible to determine the likelihood of finding an electron in a specific region around the nucleus. The quantum mechanical model represents the most sophisticated understanding of atomic structure we have to date. It incorporates principles of wave-particle duality, uncertainty, and probability to describe the interactions and behaviors of subatomic particles in a far more nuanced way than earlier models could. Today, this model forms the cornerstone of modern chemistry, physics, and materials science, providing a framework for exploring everything from chemical reactions to the fundamental forces that govern the universe. The journey to understanding atomic structure is one marked by countless experiments, theoretical breakthroughs, and paradigm shifts. From the early speculative notions of philosophers to the sophisticated quantum mechanical model that governs modern science, the development of atomic theory is a testament to the power of inquiry, experimentation, and the relentless pursuit of knowledge. What began as a philosophical idea about the nature of matter has evolved into a sophisticated scientific framework that continues to shape our understanding of the universe and drive innovation in fields ranging from medicine to technology to space exploration. The discovery of isotopes was a groundbreaking event in the history of science, profoundly reshaping our understanding of atomic theory. It was a pivotal moment that forever altered how we perceive the building blocks of matter by introducing the realization that atoms of the same element can exist in different forms. This revelation emerged in the early 20th century, during a period when scientists were making rapid advancements in atomic theory. Prominent researchers such as Frederick Soddy and J.J. Thomson played crucial roles in unraveling the mysteries of atomic structure, revealing that atoms of a given element are not necessarily identical, as had once been believed. Instead, they could vary in terms of mass, despite having the same number of protons in their nuclei. Isotopes, the term used to describe these variants of elements, represent a fascinating aspect of atomic behavior. These are atoms that, while having the same number of protons, which defines the element, possess different numbers of neutrons. This small, yet significant difference in neutron count results in atoms of the same element having different atomic masses. This breakthrough opened up a whole new realm of possibilities in scientific research, and its implications rippled through a variety of disciplines, from chemistry and physics to medicine and environmental science. Before the discovery of isotopes, the prevailing atomic theory was grounded in the belief that all atoms of a particular element were identical in both structure and mass. The idea of atomic uniformity dominated, shaping our understanding of chemistry and the very nature of matter itself. However, the revelation of isotopes shattered this assumption. It demonstrated that elements could exist in multiple forms, each with its own unique properties, fundamentally altering the concept of atomic mass. One of the most iconic examples of isotopes is carbon, an element crucial to life on Earth. Carbon exists primarily as carbon-12 with 6 protons and 6 neutrons, but it also has isotopes like carbon-13 and carbon-14, each with a different number of neutrons. These variations led to an important shift in how scientists viewed atomic structure, emphasizing that it is far more complex and dynamic than previously understood. The discovery of isotopes was not only a theoretical milestone, but also had profound real-world applications. For example, isotopes play an essential role in the field of nuclear physics, where they are used to explore the forces that govern atomic stability and to investigate nuclear reactions such as fission and fusion. The understanding of these processes has not only expanded our knowledge of the inner workings of atoms, but has also helped us comprehend the powerful forces that drive the stars, allowing them to shine and create new elements. Isotopes have also found practical uses in medicine, particularly in radiation therapy and diagnostic techniques. For instance, radioactive isotopes are used in the treatment of cancer, while others are employed in imaging and medical scanning technologies, making them indispensable in modern healthcare. Additionally, the ability to track and study isotopes has led to breakthroughs in various scientific fields. In biochemistry, isotopes are used as tracers to study complex biochemical pathways, offering a window into the inner workings of biological systems. Similarly, archaeologists have leveraged the power of isotopic analysis to date ancient artifacts and fossils, particularly through the technique of radiocarbon dating, which has revolutionized our understanding of the past and the timeline of human history. Furthermore, the exploration of isotopes has had far-reaching consequences for our understanding of nuclear reactions. By delving deeper into the behavior of isotopes, researchers have gained invaluable insights into how nuclear fission and fusion work. These processes are not only essential to understanding energy production here on Earth, but also play a critical role in astrophysics, explaining how stars are powered and how elements are formed in the universe. The discovery of isotopes has, in many ways, propelled us toward an understanding of the cosmos that was once unimaginable. In parallel with the revelation of isotopes, another transformative tool emerged, the electron microscope. This innovation marked a revolutionary leap in atomic and molecular research, providing scientists with the ability to observe and analyze matter at an unprecedented scale. Unlike traditional light microscopes, which are constrained by the wavelengths of visible light, the electron microscope uses beams of electrons, particles with much shorter wavelengths, allowing it to examine structures at the atomic level. This breakthrough offered scientists a powerful new lens through which to investigate materials, unveiling previously hidden details of atomic arrangements, molecular structures, and even the behavior of individual atoms. The electron microscope opened up new frontiers in fields like nanotechnology, material science, and semiconductor research. Researchers could now visualize and manipulate atoms with precision, allowing them to understand how atoms bond, interact, and form complex structures. This knowledge has been pivotal in the development of advanced technologies, including the creation of new materials with unique properties and the ongoing evolution of electronics and computing. It has paved the way for innovations in everything from medicine to space exploration, where understanding atomic structures and materials at the finest scales is critical. In conclusion, the discovery of isotopes and the invention of the electron microscope were two monumental events that radically transformed our understanding of the atomic world. These breakthroughs not only enhanced our scientific knowledge, but also led to practical applications that continue to shape modern society. From the complexities of atomic behavior to the intricate dance of particles in the universe, the exploration of isotopes and the advent of electron microscopy have forever altered our perception of the natural world, unlocking new possibilities in science and technology. The advent of the electron microscope marked a revolutionary milestone in scientific exploration, allowing researchers to venture into previously uncharted territories of the microscopic world. This breakthrough technology revealed a captivating new dimension of nature's hidden processes, particularly at the atomic and molecular levels. What was once confined to the theoretical realm could now be witnessed firsthand, providing an unprecedented glimpse into the dynamic interactions that govern the building blocks of matter. Through the lens of the electron microscope, the once invisible became tangible, and the walls of abstract theory began to crumble. Scientists were no longer limited to speculating about the behavior of atoms during chemical reactions or phase transitions. Instead, they could observe these phenomena in real time, as the microscope captured interactions occurring on timescales and scales once thought beyond our reach. This empirical evidence opened the door to groundbreaking discoveries, transforming fields like chemistry and physics, and drastically enhancing our understanding of material properties, atomic behavior, and the fundamental forces shaping the universe. With the electron microscope at their disposal, scientists were empowered to challenge long-held assumptions, refine established theories, and uncover intricate details about the nature of matter. This tool acted as a bridge between the macroscopic and the microscopic, allowing researchers to unravel the mysteries of the atomic world with unprecedented precision. In many ways, the microscope became a symbol of humanity's relentless pursuit of knowledge, a tool that not only expanded our understanding, but also pushed the boundaries of what we believed was possible. By unveiling the unseen, it underscored the transformative role of technology in advancing our collective comprehension of the universe. At the heart of these advances lies the concept of nucleosynthesis, the fundamental process by which elements are formed through nuclear reactions, particularly within the cores of stars. Within these cosmic furnaces, extreme temperatures and pressures create the ideal conditions for nuclear fusion to occur. Hydrogen, the simplest and most abundant element in the universe, serves as the foundational building block. Through the process of nuclear fusion, hydrogen nuclei collide and merge, forming helium and releasing vast amounts of energy in the process. This energy fuels stars, giving them their brilliance and warmth. As stars age and burn through their hydrogen fuel, their cores begin to contract, causing temperatures to rise even further. This triggers the fusion of helium into heavier elements, such as carbon and oxygen. The process continues, with each fusion cycle producing increasingly heavier elements. The result is a diverse array of atomic nuclei, each one representing a critical step in the stellar life cycle. As stars continue to evolve, they forge elements up to iron in their cores, with each new fusion process contributing to the cosmic fabric of matter. Yet the story does not end there. Elements heavier than iron are formed through other cosmic events, particularly the explosive death of massive stars. When these stars reach the end of their life cycle, they can explode in a brilliant, violent event known as a supernova. In this cataclysmic burst of energy, the intense pressures and temperatures allow for the creation of elements beyond iron, scattering them across the cosmos. These newly formed elements enrich the interstellar medium, the vast space between stars, feeding into the cycle of cosmic creation. Over time, this enriched material coalesces to form new stars, planets, and potentially even life itself. Nucleosynthesis, therefore, plays a crucial role not only in the formation of atoms, but also in the broader evolution of the universe. It is a continuous process of creation, destruction, and rebirth, where elements are forged, recycled, and transformed, driving the ongoing expansion and development of the cosmos. The origin of all these elements can be traced back to the Big Bang, which occurred approximately 13.8 billion years ago. The event marked the birth of the universe as we know it, a colossal explosion that released vast amounts of energy, scattering particles throughout the newly forming cosmos. In the moments following the Big Bang, the universe was an incredibly hot and dense environment, filled with a chaotic soup of energy and fundamental particles. As the universe began to expand, it started to cool, setting the stage for the formation of the first atomic nuclei. Within minutes of the Big Bang, nuclear fusion began to take place. Protons and neutrons, the building blocks of atomic nuclei, emerged from this primordial energy, colliding and fusing together to form the nuclei of the simplest elements, hydrogen and helium. During this early phase, known as Big Bang nucleosynthesis, approximately 75% of the universe's matter became hydrogen, while about 25% transformed into helium. This initial creation of light elements laid the groundwork for the more complex atoms that would follow, eventually contributing to the formation of stars, galaxies, and all the matter that populates the universe today. However, it wasn't until several 100,000 years later that the universe cooled enough to allow electrons to combine with atomic nuclei, forming the first neutral atoms. This crucial process, known as recombination, enabled photons, particles of light, to travel freely through the cosmos. The release of these photons gave birth to the cosmic microwave background radiation, a faint but ever-present relic of the universe's infancy, which still permeates space today. These first atoms, mainly hydrogen and helium, set the stage for the subsequent formation of the first stars and galaxies. Within these stellar bodies, nuclear fusion would take center stage, forging heavier elements and enriching the universe with the building blocks of matter. It was within these stars that the conditions necessary for nucleosynthesis were perfected, setting off a chain of events that continues to shape the universe as we know it. The creation of elements, from the smallest atoms forged in the first moments of the Big Bang to the heavier elements produced in stars and supernovae, has played a pivotal role in shaping the universe's evolution. From the formation of galaxies to the development of life on Earth, nucleosynthesis has been the driving force behind the cosmos's continuous cycle of transformation. As we continue to explore the depths of space and the microscopic world, our understanding of these processes expands, offering us profound insights into the fundamental nature of reality itself. The pursuit of knowledge, propelled by technologies like the electron microscope, is an ongoing journey, one that bridges the gap between the visible and the invisible, the known and the unknown, guiding us ever deeper into the mysteries of the universe. The journey from the Big Bang to the formation of the first atoms is a story of profound transformation, setting in motion the creation of the complex and vibrant universe that we now call home. In the beginning, only the simplest elements, hydrogen, helium, and trace amounts of lithium, were present. Over billions of years, these humble beginnings evolved through a series of processes that would give birth to the intricate cosmic structures we observe today. The creation of elements heavier than hydrogen and helium is intimately tied to the life cycles of stars. These celestial bodies, undergoing extraordinary transformations throughout their existence, are the cosmic factories where the universe's most essential elements are forged. This transformation begins with nuclear fusion, a process where lighter elements are forced together under extreme pressures and temperatures, forming heavier elements in the core of the star. In the early stages of a star's life, during what is known as the main sequence phase, hydrogen nuclei undergo fusion to form helium. This process releases vast amounts of energy, which counteracts the star's gravitational collapse, allowing it to shine for millions or even billions of years. But eventually, stars exhaust their hydrogen fuel, signaling the end of their main sequence phase. This marks the beginning of a new chapter in their evolution, as the fusion process accelerates to produce heavier elements. At this point, stars fuse helium into heavier elements such as carbon and oxygen. These reactions continue, progressing through a cascade of increasingly complex nuclear processes, creating elements up to iron. However, the production of elements beyond iron, such as gold, uranium, and platinum, requires conditions far more extreme than those found in the typical stellar interior. These elements are formed during some of the most cataclysmic events in the universe: supernova explosions and the collision of neutron stars. As a massive star nears the end of its life, it undergoes a dramatic transformation. It expands into a red giant, a phase in which the outer layers of the star swell to enormous sizes, cooling and reddening. The intense pressures within these stars enable the fusion of even heavier elements, such as silicon, sulfur, and calcium, up until the formation of iron. But iron itself cannot sustain fusion in the same way lighter elements can. It doesn't release energy when fused. This marks the star's death sentence. The internal pressure can no longer hold up against the force of gravity, and the star collapses inward, triggering a supernova. A supernova is a breathtakingly violent event, a cosmic explosion so powerful it can briefly outshine an entire galaxy. It releases enormous amounts of energy, scattering the outer layers of the star into the surrounding space. In the aftermath, these explosions create the ideal conditions for the formation of elements much heavier than iron through a process known as rapid neutron capture, or the R process. This is where elements such as gold, uranium, and other precious metals are created in vast quantities. The elements forged in these stellar explosions are ejected into space, enriching the interstellar medium. But the story doesn't end there. Neutron star mergers, when two incredibly dense remnants of massive stars collide, have been discovered to be another significant source of these heavy elements. These catastrophic events produce even more extreme conditions, providing the necessary environment for the R process to occur once again. When these two neutron stars merge, they release an incredible burst of energy, further scattering the newly created elements into space, where they can become incorporated into new stars, planets, and eventually even life forms. In this way, stars are not just the sources of light and heat, but also the crucibles in which the elements essential to life are created. Through a continuous cycle of birth, evolution, and death, stars and their explosive ends contribute to the chemical evolution of the universe itself. As supernovae explode and neutron stars collide, they seed the cosmos with the very building blocks necessary for the formation of new stars and planetary systems, eventually giving rise to life as we know it. This cosmic process of stellar birth and death is crucial to understanding how the universe came to be as it is. When we look at the elements that make up our bodies, carbon, oxygen, nitrogen, iron, and so on, it's humbling to realize that nearly 75% of the elements in our bodies were forged in the hearts of stars. Elements that were later scattered across the universe when those stars exploded as supernovae. In essence, we are made of stardust, a part of a larger cosmic cycle that has been unfolding for billions of years. The explosions of supernovae and the collisions of neutron stars are not merely cataclysmic events. They are the catalysts for life, dispersing the very materials that would eventually form planets, stars, and everything we see around us. Thus, the universe's chemical evolution is a story of transformation, where the most fundamental building blocks of matter are constantly being created, destroyed, and reformed. Every time a star is born, evolves, and dies, it contributes to this ongoing process, enriching the cosmos with the ingredients for life, making the universe a vast, interconnected system of creation and destruction, a never-ending cycle that continues to this day. In the vast, mysterious expanse of our universe, the violent energy released from cosmic explosions plays a critical role in shaping the intricate dynamics of galaxies. These explosive events, known as supernova, generate powerful shock waves that ripple through the surrounding space, compressing nearby gas clouds. This compression is not just a fleeting effect. It ignites the birth of new stars, fostering an ongoing cycle of stellar creation, death, and rebirth. Such phenomena are essential for recycling materials within the universe, propelling the endless evolution of the cosmos. Supernovae, particularly the Type 2a variety, which occur in binary systems where a white dwarf pulls in matter from a companion star, also serve a pivotal role in our understanding of the universe's grand expansion. These stellar explosions act as standard candles for astronomers, offering a reliable method of measuring cosmic distances and the brightness of far-off stars. By observing the light emitted from these supernovae and calculating their distance, scientists can gain profound insights into the rate at which the universe is expanding. This, in turn, sheds light on the complex interactions between dark energy and the larger structure of the universe. Through this process, supernovae not only influence the chemical composition of the universe, but also provide essential clues about its vast, evolving nature. Black holes, those enigmatic cosmic objects, exert an influence on their surroundings far beyond what is immediately apparent. Formed from the remnants of massive stars that have exhausted their nuclear fuel, black holes are regions in space where gravity is so intense that not even light can escape. At the center of a black hole lies a singularity, an incredibly dense point, surrounded by an event horizon, the boundary beyond which nothing can return. While their role in the direct creation or destruction of atoms may not be obvious at first glance, their impact on the atomic world is profound. As matter spirals toward a black hole, it forms an accretion disk, a rotating ring of material that is heated to extreme temperatures. This heating produces intense radiation that can affect nearby atoms, stripping them of electrons and disrupting their atomic bonds. Essentially, black holes contribute to the breakdown and transformation of matter at the atomic level. Furthermore, the gravitational influence of black holes extends beyond simply swallowing matter. It can trigger or suppress the formation of new stars by affecting the collapse of nearby gas and dust clouds. The life cycle of stars, birth, death, and supernova explosions creates heavier elements within their cores. When these stars die, they release these elements into the cosmos, providing the building blocks for new stars, planets, and eventually life itself. The most massive black holes, known as supermassive black holes, reside at the centers of galaxies. Their gravitational pull is so intense that it can create high-energy phenomena like gamma-ray bursts, which have the potential to disrupt the atomic structures of matter on a vast scale. While black holes do not actively destroy atoms in the conventional sense, their immense gravitational forces and the intense radiation they emit shape the very fabric of the universe, driving a continual cycle of destruction and creation. In a universe governed by both matter and energy, understanding quantum mechanics is crucial to comprehending the behavior of atoms, particularly the electrons that occupy them. Traditional models once depicted electrons as small particles orbiting a nucleus in fixed paths, like miniature planets orbiting a sun. However, quantum theory revolutionized this understanding by introducing the concept of wave-particle duality. According to quantum mechanics, electrons do not follow fixed orbits. Instead, they exist in a state of probability, described by a wave function that outlines the likelihood of finding an electron in a particular location at any given time. This probabilistic nature means that electrons occupy specific energy levels, or orbitals, within an atom. These orbitals are not random, but rather take on distinct shapes, spherical, lobed, and so on, each representing a region in space where the electron is most likely to be found. What is fascinating is that these orbitals are quantized, meaning that electrons can only exist in certain discrete energy states. When an electron transitions between these states, it either absorbs or emits energy, often in the form of light. This process is responsible for the characteristic spectra observed in different elements, and it plays a crucial role in the understanding of atomic structure and behavior. Thus, the intricate relationships between supernovae, black holes, and quantum mechanics offer a profound view into the cosmic processes that govern the universe. These forces not only shape the matter that makes up galaxies, stars, and planets, but also influence the very laws of physics that determine the behavior of atoms and the fundamental forces of nature. In this ever-evolving cosmic drama, the interplay of creation, destruction, and rebirth continues to unfold on a scale beyond human comprehension, reminding us of the infinite complexity and beauty of the universe itself. The Pauli exclusion principle, a cornerstone of quantum mechanics, plays an essential role in explaining the intricate arrangement of electrons within an atom. This principle asserts that no two electrons can occupy the same quantum state at the same time, which profoundly influences how electrons populate orbitals. As a result, electrons fill orbitals in a precise order, a process that not only shapes the chemical properties of elements, but also governs how these elements interact and bond with one another. The specific arrangement of electrons, therefore, dictates the behaviors of atoms and molecules, determining how they react chemically and physically in the world around us. This fundamental principle extends beyond the confines of the atom, influencing the behavior of matter and energy on a far larger scale. From the seemingly mysterious phenomenon of superconductivity to the technological marvels of semiconductors, quantum mechanics is central to the function of many modern technologies. Indeed, quantum theory provides a window into the very nature of the universe, offering insights not only into the workings of the microscopic world, but also the forces that shape the macroscopic realm. It is this same theory that underpins much of our understanding of the cosmos, from the behavior of the smallest particles to the largest celestial bodies. One of the most captivating and mind-bending concepts of quantum mechanics is wave-particle duality. This principle reveals that particles, such as electrons and photons, can exhibit characteristics of both waves and particles depending on the circumstances. This duality challenges our conventional understanding of the physical world, where objects are typically categorized as either particles or waves. At the quantum level, however, the distinction between these two states becomes blurred. Under certain conditions, particles behave like waves, and under others, they manifest as discrete particles. This wave-particle duality is intricately tied to the structure of the atom itself. Unlike the familiar image of planets orbiting the sun, electrons in an atom do not follow fixed circular paths. Instead, they exist in regions of probability, referred to as orbitals. These orbitals can be thought of as clouds where electrons are most likely to be found, but their precise location at any given moment is uncertain. Scientists cannot pinpoint the exact position of an electron, but they can calculate the probability of where it might be located at any moment. This concept is expressed through wave functions, which represent the wave-like nature of electrons. Perhaps one of the most famous experiments illustrating wave-particle duality is the double-slit experiment. When particles, such as electrons, are directed through two closely spaced slits, they produce an interference pattern, a phenomenon typically associated with waves. The pattern emerges when both slits are open, suggesting that the particles behave like waves as they pass through the slits. However, when observed, the particles act as discrete entities, striking a screen as individual points, much like how we would expect particles to behave. This experiment, in its simplicity, captures the profound paradox at the heart of quantum mechanics, the simultaneous wave and particle nature of subatomic particles. The implications of this experiment are far-reaching. They challenge our most basic assumptions about the nature of reality itself. For in the quantum world, the act of measurement can alter the behavior of the very system being observed. The notion that particles can exist in multiple states at once, and that their behavior can change based on how they are observed, creates a reality that is deeply counterintuitive to our everyday experiences. In essence, quantum mechanics doesn't just redefine our understanding of atomic structure. It reshapes our very understanding of the nature of reality, showing us a world far stranger and more complex than we ever imagined. From the basic building blocks of matter to the technologies that define our modern world, quantum mechanics provides the framework that links the microcosmic to the macroscopic. It is a theory that continues to inspire awe and wonder, pushing the boundaries of human knowledge and challenging us to rethink the universe itself. However, when scientists attempt to observe which slit an electron passes through, the interference pattern disappears. Instead, the electron behaves more like a particle. This observation highlights a profound phenomenon in quantum mechanics. The very act of measurement alters the behavior of particles at the atomic and subatomic levels. It is a striking example of how the universe operates in a way that defies traditional logic. The concept of wave-particle duality, where particles such as electrons exhibit both wave-like and particle-like properties depending on how they are measured, becomes essential to understanding the nature of the quantum world. This duality isn't just a quirky aspect of atomic behavior. It serves as the cornerstone for fields like quantum computing and chemistry. By acknowledging and exploring the behavior of particles in this paradoxical way, scientists can unlock deeper insights into the interactions of matter and energy at the most fundamental levels. This understanding challenges our everyday notions of reality. It suggests that the universe is intricately interconnected, with the act of observing itself influencing the fabric of reality. The idea that simply looking at a system can alter its behavior has profound implications, opening up a new way of thinking about the relationships between observer and observed. The concept has become a focal point for innovation, sparking new technologies and shaping our evolving view of science and the universe. Central to these discussions is Heisenberg's uncertainty principle, a theory that revolutionized our understanding of quantum mechanics. Proposed by the German physicist Werner Heisenberg, this principle states that it is impossible to simultaneously know both the exact position and momentum of a particle with complete precision. The more accurately we try to measure one of these properties, the less accurately we can determine the other. This inherent uncertainty in the behavior of particles stands in stark contrast to classical physics, which assumes that precise measurements are always possible. At the atomic level, this principle becomes particularly clear. Take the example of electrons orbiting the nucleus of an atom. Their exact location cannot be pinpointed. Rather than existing in a single, fixed position, electrons are found in regions where they are most likely to be located. These regions are known as atomic orbitals. These orbitals represent the probability of finding an electron in a certain space, not a precise path it follows. In essence, electrons are better understood not as particles traveling along a determined trajectory, but as existing in a cloud of probabilities. This probabilistic nature of atomic behavior profoundly alters the way scientists conceptualize the microcosm. It challenges the deterministic outlook that classical physics provided, inviting a deeper exploration into the chaotic and interconnected rules that govern the atomic realm. The uncertainty principle leads to unexpected and fascinating phenomena, like wave-particle duality, where the behavior of electrons and other subatomic particles is influenced by the method of observation. Moreover, the uncertainty principle forces us to rethink the very nature of reality. It tells us that at the quantum level, particles don't possess fixed properties until they are measured or observed. This realization disrupts classical notions of objectivity and stability, opening the door to a new realm of scientific inquiry where the boundaries between observation and reality blur. Quantum mechanics, therefore, is not just a theoretical framework. It offers a radically different way of understanding the universe. It implies that reality at the atomic and subatomic level operates according to principles vastly different from the orderly, predictable world we encounter in everyday life. This insight has far-reaching consequences, influencing not only the development of quantum technologies, but also our basic understanding of what matter is and how it behaves. In this context, quantum entanglement stands out as another mind-boggling phenomenon that continues to defy our classical intuitions. When two or more particles become entangled, their states are so deeply linked that the state of one particle immediately affects the state of another, no matter how far apart they are in space. This connection happens instantaneously, even if the particles are light years away from each other. The idea that particles can be connected across vast distances challenges everything we know about space, locality, and the speed of information transfer. When one particle in an entangled pair is observed, the state of the other particle is determined simultaneously, regardless of the distance between them. This instantaneous connection raises profound questions about the nature of causality and the limits of communication. For instance, if two entangled particles are measured, the results are perfectly correlated, even if they are separated by unimaginable distances. This suggests a level of synchronization that cannot be explained by classical physics, leading to intriguing discussions about the possibility of instantaneous communication over long distances. The implications of quantum entanglement extend far beyond theoretical physics. They have practical applications, particularly in the realm of quantum computing. Entanglement allows quantum computers to perform complex calculations at speeds that classical computers cannot match. In a quantum computer, entangled quantum bits, or qubits, can represent multiple states simultaneously, enabling them to solve problems that would take classical computers millions of years. This could transform industries from cryptography to artificial intelligence, offering solutions that are currently unimaginable with conventional technology. Quantum entanglement also contributes to the ongoing investigation into the fundamental forces of nature. It suggests that particles, even those that appear to be independent, may not be as isolated as they seem. At the most basic level, particles could be interconnected in ways that are not yet fully understood. This insight challenges the classical view of a universe composed of independent entities and invites new ways of thinking about how matter and energy interact. As researchers continue to explore these interconnections, they may uncover breakthroughs that reshape our understanding of everything from atomic interactions to the fundamental forces that govern the universe. The evolution of quantum theory has transformed our understanding of atomic and subatomic particles in profound ways. In the early 20th century, scientists realized that classical physics could not fully explain the behavior of tiny particles like electrons. This led to the development of quantum theory, which introduced concepts like wave-particle duality. These groundbreaking ideas changed the way scientists thought about the very nature of particles, providing the tools to describe atomic interactions in ways that classical models could not. Quantum mechanics also led to the creation of more accurate models of the atom. By introducing the concept of quantum states, scientists could predict the arrangement of electrons around an atom's nucleus. This understanding explained why different elements exhibit specific chemical properties, leading to the development of the quantum mechanical model of the atom. This model replaced earlier classical theories which failed to account for the complexities and behaviors observed in atomic systems. Quantum theory continues to shape the direction of scientific research, opening new avenues for discovery and technological advancement. As we continue to explore the strange and fascinating behaviors of particles at the quantum level, we are not only redefining our understanding of physics, but also laying the groundwork for future breakthroughs that could revolutionize technology and our understanding of the universe itself. Advancements in quantum theory have unleashed a wave of technological innovations that have not only reshaped our understanding of the universe, but also revolutionized the way we interact with the world around us. These breakthroughs have opened new frontiers in science and technology, leading to the emergence of cutting-edge fields such as quantum computing and quantum cryptography. These innovations are not just theoretical concepts, but have already begun to impact society, offering transformative possibilities that were once thought to be the stuff of science fiction. At the heart of these technologies lie the principles derived from quantum mechanics, a branch of physics that describes the behavior of particles on the smallest scales of energy levels of atoms and subatomic particles. Quantum computing, for example, leverages the unique properties of quantidates, such as superposition and entanglement, to perform computations in ways that traditional computers based on classical mechanics could never achieve. In quantum computers, a bit does not simply represent a 0 or 1, but can exist in multiple states simultaneously, leading to an exponential increase in computational power. This capacity could enable breakthroughs in fields ranging from artificial intelligence to complex scientific simulations that could potentially solve some of humanity's most pressing problems. Similarly, quantum cryptography, which is grounded in the principles of quantum mechanics, promises to revolutionize information security. Unlike classical cryptography, which relies on mathematical algorithms that can be cracked with enough computational power, quantum cryptography uses the fundamental properties of quantum systems to create encryption methods that are theoretically unbreakable. This method takes advantage of the fact that quantum information cannot be copied or measured without altering the system itself, ensuring that any attempt at eavesdropping would be immediately detectable. In recent years, atomic research has also uncovered some of the most fascinating phenomena ever observed in science, such as quantum entanglement and superposition. These phenomena challenge our classical intuitions about reality, defying the laws of everyday experience and hinting at a deeper, more interconnected structure of the universe. Quantum entanglement, for example, suggests that two particles can become instantaneously connected, no matter the distance between them, such that the state of one particle can affect the state of another. This idea fundamentally challenges our understanding of space and time and has profound implications for the future of communication and computing. By studying these phenomena, scientists are gaining insights into the fundamental nature of matter and energy, enriching our understanding of atomic behavior. Furthermore, the exploration of these quantum effects inspires new avenues of inquiry that stretch across a wide array of disciplines, from material science to cosmology, opening up new realms of possibility for innovation and discovery. It also underscores the interconnectedness of all scientific knowledge, as discoveries in one field often lead to breakthroughs in another, revealing a tapestry of scientific ideas that is richer and more complex than ever before. Central to our understanding of atomic behavior is the role of the four fundamental forces of nature. These forces govern the interactions between atoms and particles, shaping the very structure and behavior of matter. Gravity, although the weakest of these forces, is perhaps the most familiar to us. It governs the large-scale structure of the universe, pulling matter together to form stars, planets, and galaxies. Despite its significant role on cosmic scales, gravity is largely negligible on the atomic level, where its effects are overshadowed by the other forces. The second fundamental force, the electromagnetic force, is much stronger than gravity and plays a pivotal role in the interactions between charged particles, such as protons and electrons. This force is responsible for holding electrons in their orbits around the nucleus of an atom, enabling the formation of chemical bonds and giving rise to the phenomena of electricity, magnetism, and light. These phenomena are essential to our understanding of atomic interactions, material properties, and even the behavior of light itself, which is a form of electromagnetic radiation. Next is the weak nuclear force, a crucial player in the processes of radioactive decay and nuclear fusion. The weak force facilitates interactions between particles like neutrinos and enables certain types of nuclear reactions that are vital for the life cycles of stars. This force, though not directly responsible for binding atoms together, plays an essential role in the synthesis of elements in the universe and the energy processes that power stars. Finally, the strongest of the fundamental forces is the strong nuclear force, which binds protons and neutrons together within the nucleus of an atom. This force operates at incredibly short ranges, typically on the scale of about 1 femtometer, a millionth of a billionth of a meter. Yet it is powerful enough to overcome the electromagnetic repulsion between the positively charged protons, ensuring the stability of atomic nuclei. Without the strong nuclear force, the very existence of atoms, and thus all matter, would not be possible. Together, these fundamental forces govern the behavior of atoms and their interactions, creating the physical universe as we know it. From the formation of stars to the chemistry that drives life, these forces are responsible for the underlying structure and dynamics of all matter. Electromagnetic interactions, in particular, are central to the way atoms bond and form molecules. The electromagnetic force arises from the attraction between the positively charged protons in the nucleus and the negatively charged electrons that orbit around it. When two atoms approach each other, their electrons and nuclei experience electromagnetic interactions, creating the potential for chemical bonds to form. These bonds are the foundation of chemistry and life itself. There are two primary types of chemical bonds that are influenced by electromagnetic force: ionic bonds and covalent bonds. In an ionic bond, one atom donates an electron to another, resulting in the formation of positively and negatively charged ions. The electromagnetic attraction between these oppositely charged ions holds them together. A classic example of this type of bond is seen in table salt, where sodium donates an electron to chlorine, forming a strong ionic bond due to the charge difference between the two elements. In contrast, covalent bonds occur when two atoms share electrons, allowing both atoms to achieve a more stable electron configuration. This sharing lowers the overall energy of the system, creating a more stable arrangement. The balance of electromagnetic forces between the nuclei of the atoms and the shared electrons keeps the atoms bonded together. A well-known example of this is the water molecule, where each hydrogen atom shares an electron with the oxygen atom, creating a stable combination thanks to these shared electromagnetic interactions. These fundamental forces and the bonds they create are at the core of all matter, from the simplest hydrogen atom to the most complex molecules that form life. Understanding these interactions is crucial not only to the fields of physics and chemistry, but also to a wide range of disciplines that seek to unravel the mysteries of the universe, from the microscopic world of atoms to the vast expanses of the cosmos. Each discovery builds upon the last, showing us how deeply interconnected the forces of nature truly are. Electromagnetic forces play a vital role in many of the fundamental phenomena of the universe, affecting everything from simple molecules to complex biological systems. One notable example is the role they play in hydrogen bonding. While hydrogen bonds are weaker than covalent bonds, they still have significant impacts on the properties of water and key biological molecules like DNA. These interactions serve as a testament to how electromagnetic forces shape the very structure of matter. From the smallest atoms to the most intricate molecular arrangements, electromagnetic forces are at the heart of countless chemical reactions and molecular behaviors. Their influence is far-reaching, and understanding them deepens our appreciation of the underlying forces that govern the universe. The strong nuclear force, one of the four fundamental forces of nature, is pivotal to the behavior of atomic nuclei. This force binds protons and neutrons together within an atom's nucleus. Protons, being positively charged, naturally repel one another due to the electrostatic force. Without the strong nuclear force, these protons would fly apart and atomic nuclei would not be able to exist. The strong nuclear force, however, works to counteract this repulsion, holding the nucleus together. While this force is incredibly powerful, it operates only over very short distances, roughly the size of an atomic nucleus. Interestingly, the strong nuclear force is transmitted by particles known as gluons, which bind quarks, the fundamental building blocks of protons and neutrons. Even a small atomic nucleus containing fewer than a dozen protons requires additional neutrons to help balance the repulsive forces between the positively charged protons. Neutrons serve as a kind of buffer, enabling protons to remain bound together within the nucleus. As the size of the atomic nucleus increases, so too does the need for more neutrons to maintain stability. If the number of neutrons is too high or too low, the nucleus will become unstable and may undergo radioactive decay. The strong nuclear force is not only crucial for the existence of atomic nuclei, but also for the creation and stability of elements. Without it, the universe would be a far less diverse place, with fewer elements and compounds. The balance that the strong nuclear force provides is essential not just for holding atoms together, but for the very structure of the universe itself. In contrast, the weak nuclear force operates on a much smaller scale, but is equally important. It plays a key role in atomic decay, particularly through processes like beta decay. Unlike the strong nuclear force, which binds protons and neutrons within the nucleus, the weak force is responsible for transforming one type of particle into another. This transformation is critical for the stability of certain isotopes and for the creation of new elements. For instance, during beta decay, a neutron in an unstable atomic nucleus changes into a proton, emitting a beta particle, which is essentially a high-energy electron. This process occurs because the weak nuclear force enables quarks, the fundamental constituents of protons and neutrons, to change. In this case, a down quark in the neutron is converted into an up quark, resulting in the transformation of the neutron into a proton. This change alters the atomic number of the element, effectively creating a new element. Additionally, a neutrino, a nearly massless particle, is emitted to carry away some of the energy released during the decay. The weak nuclear force also plays a significant role in the interactions of neutrinos, particles that are often elusive due to their ability to travel vast distances without interacting with matter. Neutrinos are notoriously difficult to detect, but they are essential for understanding astrophysical processes and certain types of reactions in the universe. Despite their fleeting interactions, neutrinos contribute to the energy balance of stars, including the mechanisms that power their internal processes. Together, these fundamental forces, electromagnetic, strong nuclear, and weak nuclear, work in concert to shape the structure and behavior of matter. Their effects are felt on every scale, from the behavior of individual atoms to the workings of complex biological systems. These forces define not only the properties of matter, but also the stability of the universe itself. As scientists continue to unravel their mysteries, our understanding of these forces only deepens, opening up new possibilities for discovery and insight into the fabric of reality. In the vast, intricate dance of the cosmos, weak nuclear forces play a crucial yet often overlooked role in shaping the universe as we know it. At its core, these forces are responsible for atomic decay processes that occur within stars, fueling the release of energy we observe as starlight. Without the weak nuclear forces, however, the universe would be drastically different from what it is today. Isotopes which undergo weak interactions would not exist, or they would remain unstable, leading to fewer elements forming as a result of gravitational collapse. This, in turn, would significantly impact the chemical diversity of the universe and hinder the creation of the wide array of materials essential for life and celestial development. But the significance of weak nuclear forces extends far beyond the simple existence of isotopes. These forces tap into the very foundation of particle physics and the evolutionary processes that have sculpted the universe. The interaction of particles, from the tiniest subatomic elements to the largest galactic structures, hinges on the delicate interplay of forces like the weak nuclear interaction. Understanding this force helps scientists trace the origins of the universe and the dynamics of its ongoing evolution. Amidst the discussion of atomic forces and the building blocks of matter, another intriguing counterpart emerges: antimatter. While ordinary matter is composed of particles such as electrons, protons, and neutrons, antimatter consists of corresponding antiparticles. For example, the antimatter equivalent of an electron is a positron, which carries a positive charge instead of a negative one, but has the same mass. This fundamental difference in charge leads to profound and often dramatic consequences when antimatter interacts with normal matter. When matter and antimatter meet, the result is a cataclysmic annihilation that releases an extraordinary amount of energy. In this annihilation, both particles and antiparticles obliterate each other, converting their mass entirely into energy, as predicted by Einstein's iconic equation, E equals mc². The energy produced in these collisions is immense, a reminder of just how much potential is stored within even the smallest quantities of matter and antimatter. Such interactions raise tantalizing questions about the nature of the universe, such as why there seems to be an overwhelming abundance of matter compared to the almost non-existent presence of antimatter. Although scientists have succeeded in creating tiny amounts of antimatter in laboratories, it remains incredibly rare in the natural universe. This scarcity starkly contrasts with the abundance of ordinary matter, sparking the age-old mystery. Why is the universe seemingly biased towards matter? Understanding the elusive nature of antimatter not only deepens our understanding of physics, but also holds promise for groundbreaking technological advancements, including advanced medical imaging and even the development of potential new energy sources. The journey into the mysteries of atomic interactions and antimatter brings us closer to uncovering the deeper truths of our universe, helping to answer fundamental questions about its origin, composition, and ultimate fate. Yet at the heart of these investigations lies a critical truth. Atoms are the very building blocks of matter. They form the foundation for everything we can see and touch, from the smallest grains of sand to the largest galaxies. The birth of the universe, approximately 13.8 billion years ago, began with the explosive event known as the Big Bang. This cataclysmic moment marked the creation of a hot and dense state that began to cool, eventually giving rise to the first simple atoms, primarily hydrogen and helium. These primordial atoms formed the seeds of everything that followed. As the universe expanded and cooled, gravity began to work its magic, pulling atoms together into dense regions of matter. These regions eventually became the gas clouds, or nebula, where stars would be born. Within the core of these stars, a process known as nuclear fusion ignites, turning hydrogen into helium and later heavier elements. This stellar furnace is responsible for producing the building blocks of the universe's chemical diversity. As stars reach the end of their life cycles, many undergo dramatic supernova explosions, scattering the elements they've created throughout space. This cosmic scattering enriches the interstellar medium with the materials necessary to form new stars, planets, and other celestial bodies. The death of one generation of stars gives rise to the next, continuing the eternal cycle of creation, transformation, and destruction. This ongoing process of atomic interactions has shaped the universe for billions of years, guiding the formation and evolution of galaxies, stars, planets, and more. It is through these atomic forces that we observe the vast complexity of the cosmos, an intricately woven tapestry where every star, every planet, and every galaxy is the product of countless atomic interactions. These forces govern not only the birth of new celestial bodies, but also their evolution across the eons, ensuring that the universe remains dynamic and ever-changing. The role of atoms in the universe goes far beyond just their presence in stars and galaxies. They are the foundation of the different states of matter, solids, liquids, and gases, all of which exhibit distinct properties due to the atomic arrangements within them. This diversity in the behavior of matter is what allows for the rich variety of substances we see around us, from the smallest rock to the most massive planet. On Earth, for example, the combination of liquid water, carbon-based life forms, and a variety of minerals is the direct result of the unique atomic structures created in past generations of stars. In the early universe, only the simplest atoms, hydrogen and helium, existed. As the universe cooled, these atoms began to coalesce under the force of gravity, forming the first stars. Within these stars, nuclear fusion began, creating the first heavy elements such as carbon, oxygen, and nitrogen. The elements produced in stars were scattered into space during supernova events, enriching the cosmos with the material needed for the formation of new stars and planets. The cycle of star formation, stellar death, and the dispersal of elements through space continues to shape the universe's chemical diversity, ultimately influencing the development of planets like Earth. It is through the interactions of atoms, their ability to form complex molecules, and the energy produced through nuclear processes that the universe continues to evolve. From the very beginning, atoms have been the fundamental forces driving the ongoing expansion of the cosmos, shaping everything from the stars in the sky to the life that exists on our planet. This delicate balance of atomic interactions forms the backbone of the universe, reminding us of the beauty and complexity that lies in the smallest building blocks of existence. The study of atoms goes far beyond merely understanding the basic components of matter. It's a journey that spans across the vast expanse of the universe, revealing how these minute building blocks influence the structure of everything around us. Atoms don't just make up the physical objects we see. They are intimately tied to the fundamental forces and phenomena that govern the cosmos. Take electromagnetic radiation, for example. The atoms within stars and other celestial bodies emit and absorb this radiation, acting as cosmic beacons that allow us to peer into the heart of the universe. This radiation gives us a window into the properties of distant stars and galaxies, offering invaluable insights into their composition, behavior, and the way the universe has evolved over billions of years. Through this lens, atoms reveal themselves not just as fundamental components of matter, but as integral threads woven into the very fabric of the universe. Dark matter and dark energy are two of the most mysterious and essential components of the universe. These enigmatic forces hold the key to understanding the universe's structure and its ultimate fate. Dark matter, which constitutes roughly 27% of the universe's total mass, is invisible to us. It does not emit, absorb, or reflect light, making it impossible to detect through conventional means. Yet, its presence is unmistakable when we observe the gravitational effects it has on visible matter. It plays a critical role in maintaining the structure of galaxies by helping to keep them bound together. Without dark matter, the galaxies we see today would be unable to maintain their form. Their rotational speeds would be far too high for the visible matter to stay intact. Although we cannot directly observe dark matter, its influence is visible in the way galaxies rotate and through the phenomenon of gravitational lensing, where the light from distant objects bends around massive clusters of unseen matter. On the other side of the cosmic equation is dark energy, which makes up a staggering 73% of the universe. This mysterious force is believed to be responsible for the accelerating expansion of the universe. Unlike gravity, which attracts objects toward one another, dark energy exerts a repulsive force on a cosmic scale, pushing the fabric of space itself apart. The discovery of this phenomenon in the late 20th century was nothing short of revolutionary. Observations of distant supernovae revealed that the universe wasn't just expanding, it was expanding at an ever-increasing rate. While the exact nature of dark energy remains poorly understood, many scientists theorize that it could be a fundamental property of space itself, perhaps related to the concept of vacuum energy in quantum physics. Although dark matter and dark energy remain elusive in their full nature, their influence on normal matter, like the atoms that make up stars, planets, and even living organisms, is undeniable. Dark matter's gravitational pull affects the motion of normal matter, keeping galaxies intact and influencing their evolution. However, normal matter does not interact directly with dark energy. Instead, dark energy influences the broader dynamics of the universe's expansion, driving galaxies and all other cosmic entities further apart. Together, these three cosmic forces, normal matter, and dark energy, shape the evolution of the universe, dictating everything from the formation of galaxies to the vast structures that define the cosmos. The interaction of these forces determines the future of the universe and how its celestial entities will evolve, live, and eventually meet their end. As scientists continue to explore the mysteries of dark matter and dark energy, they seek to better understand their roles in the complex and ever-changing tapestry of the universe. But beyond these invisible forces, atoms themselves hold another crucial key to unraveling the potential for life beyond Earth. The distribution and abundance of atoms are essential for determining where life might exist elsewhere in the universe. Atoms are the building blocks of all matter, and the specific combinations of these atoms create molecules that are necessary for the existence of life as we know it. Among the most critical elements for life are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, often referred to as the life elements. The availability and distribution of these elements in various environments play a vital role in determining whether life could arise and thrive there. When we look to the stars and planets in our quest for extraterrestrial life, we focus on areas rich in these essential atoms. Carbon, in particular, is the cornerstone of organic molecules and is the backbone of all known life. The discovery of organic compounds on other planets and moons is an encouraging sign, indicating that conditions might be right for life to exist beyond our planet. Whether on Mars, Europa, or distant exoplanets, the presence of these fundamental building blocks raises the tantalizing possibility that life could exist or have once existed elsewhere in the cosmos. And so, as we peer deeper into space, we do so not just to understand the atoms that make up the universe, but to search for the possibility that these very atoms could give rise to life in places far beyond our own world. Water, a compound made up of 2 hydrogen atoms and 1 oxygen atom, stands as the cornerstone of life itself. Its critical role in sustaining life across our planet is beyond dispute. The discovery of vast bodies of liquid water, or even ice, in other celestial bodies is nothing short of thrilling. It opens the door to the possibility that life might exist, or have once existed, in places beyond Earth. However, the mere presence of water alone is not enough to determine the potential for life. Other factors, such as the planet's position relative to its star, the geological activity of its surface, and even hidden features beneath its surface, all play vital roles in shaping the prospects for life. The habitable zone of a star, also called the Goldilocks zone, is the region where conditions are just right for maintaining liquid water. It is here that planets and moons are most likely to possess the right conditions for supporting life as we know it. However, life may not always require the same environment we are familiar with. Some celestial bodies, though seemingly inhospitable at first glance, may possess subsurface features, such as water under the ice or volcanic activity, that could foster life. This shows us that the search for life should not be limited to surface conditions alone, and subsurface exploration may yield untapped potential for biological processes. Moreover, life on Earth exists in some of the most extreme environments imaginable. From the searing depths of the deep ocean trenches to the high radiation zones around volcanic fissures, Earth's resilient life forms have adapted to thrive under conditions that would be lethal to most other forms of life. This ability to survive in such diverse and extreme environments suggests that life elsewhere in the universe may not be bound by the same limitations. It raises the fascinating possibility that alien life forms might use elements or chemical processes entirely different from those we rely on here on Earth, broadening our understanding of what constitutes life. The universe, it seems, is full of surprises, and the adaptability of life may be far more versatile than we can currently imagine. As our exploration of the cosmos continues, one of the central pursuits of astrobiology will remain the search for the right atomic mixtures. Atoms, the fundamental building blocks of matter, are what allow for the extraordinary chemical diversity that defines the nature of planetary systems. Atoms are made up of protons, neutrons, and electrons, and the way these particles combine creates molecules. These molecules form through chemical bonds, and it's the specific combinations of different atoms, known as elements, that generate the vast array of chemical reactions we observe. There are more than 100 elements on the periodic table, and each one has unique properties that influence the way it interacts with other elements. For example, carbon, in particular, plays an essential role in life as we know it. Carbon atoms can bond with other elements like hydrogen, oxygen, and nitrogen, forming the complex molecules that are the building blocks of life. These molecules include amino acids, the precursors to proteins, and nucleotides, which make up genetic material. Such organic compounds are critical for the biological processes that sustain life. Stars, too, play a fundamental role in shaping chemistry. Through their immense energy, they drive the creation of complex molecules, many of which become the building blocks for life in planetary systems. The types of molecules that form depend largely on the environmental conditions on a given planet. A planet's temperature, pressure, and presence of water can dramatically alter the chemical reactions that take place, making each planet's chemistry unique. For instance, a planet closer to its sun might produce more gaseous compounds, while one farther away could see the formation of icy substances. This diversity of chemical compounds, shaped by the varying conditions across the universe, is what makes every planetary system unique. Whether it's the solid, rocky surface of Earth or the thick, gaseous clouds surrounding Jupiter, the intricate interactions between atoms form the basic chemistry of these celestial bodies. This variation in atomic configurations and their resultant compounds is the underlying factor that determines the nature of each planetary system in the cosmos. Modern science has developed advanced technologies to explore and understand these atomic interactions at an unprecedented level. One of the most remarkable tools in this area is atomic force microscopy, AFM, which allows scientists to visualize individual atoms by scanning a sharp tip over a surface. This technique has revolutionized fields like nanotechnology and material science, enabling researchers to see atomic arrangements with incredible detail. AFM is invaluable for studying the structure of materials at the atomic level, providing insights into their properties and behaviors. Another groundbreaking technique is scanning tunneling microscopy, STM. Unlike AFM, STM uses the principles of quantum tunneling to scan just above a surface without touching it. The technique captures the resulting current from this tunneling effect, enabling scientists to observe atomic-level images of surfaces. STM can even manipulate individual atoms, allowing researchers to experiment with the fundamental components of matter at the nanoscale. Then there are the colossal particle accelerators, like the Large Hadron Collider, LHC, which push the boundaries of discovery by smashing particles together at near-light speeds. These massive machines collide protons and other subatomic particles, revealing the fundamental components of matter, such as quarks and leptons. Through these high-energy experiments, physicists are uncovering the deeper workings of the universe, including the Higgs boson, a particle integral to our understanding of how particles acquire mass. This research not only expands our knowledge of the universe, but also provides insights into the origins of matter itself. Each of these technologies represents a step toward understanding the fundamental forces that shape the universe, from the atomic to the cosmic scale. As we continue to explore space and study the building blocks of life, the interplay of atoms and their chemical diversity will undoubtedly remain central to our quest to understand the cosmos and the potential for life beyond our planet. In recent years, revolutionary advancements in scientific techniques have allowed researchers to peer deeper into the atomic and subatomic worlds, offering an unprecedented understanding of matter and energy. Among the most transformative methods is laser spectroscopy, a technique that has propelled atomic research to new heights. Using high-intensity lasers, scientists can excite atoms, enabling them to observe the intricate processes of emission and absorption. This form of spectroscopy allows for detailed investigations into the energy levels of atoms and molecules, revealing critical information about their structures and behaviors. As these technologies continue to evolve, they shed light on the complexities of atomic interactions, further enhancing our grasp of the atomic realm. Particle physics in particular has opened new doors to understanding the fundamental building blocks of matter. By delving into the particles smaller than atoms, physicists have uncovered an elaborate framework describing how these particles behave and interact with one another. The discovery of particles such as quarks and leptons shattered the previous notion of atoms as indivisible units. Instead, it revealed that atoms themselves are made up of even smaller constituents, radically altering our perception of atomic structure. This newfound understanding emerged through high-energy collisions in particle accelerators, where particles are accelerated to nearly the speed of light and smashed together. These collisions recreate conditions similar to those of the universe's early moments, offering insight into the forces that govern particle interactions. Within this realm, the strong nuclear force is pivotal, holding protons and neutrons together inside the atomic nucleus. The weak force, on the other hand, governs certain types of radioactive decay. These interactions are examined in extraordinary facilities such as the Large Hadron Collider, LHC, where the most cutting-edge experiments are conducted. It was within the LHC that the elusive Higgs boson was discovered in 2012, forever altering our understanding of mass. The Higgs boson plays a critical role in explaining how particles acquire mass, a fundamental aspect of the universe's structure. The discovery has not only deepened our understanding of the cosmos, but also challenged existing models of particle physics, prompting scientists to refine the standard model of particle physics. Yet the implications of particle physics extend far beyond theory. The technologies developed for particle detection and imaging have had profound real-world applications. For instance, advancements in this field have been instrumental in medicine, particularly in cancer diagnosis and treatment. Techniques like positron emission tomography, PET scans, which rely on particle detection, have revolutionized non-invasive imaging, helping doctors identify tumors with remarkable precision. These breakthroughs underscore how exploring the atomic and subatomic worlds enhances both our scientific knowledge and the technologies that impact daily life. Atomic visualization, another vital aspect of modern science, has seen groundbreaking innovations that are reshaping our understanding of materials at the atomic scale. One of the most notable techniques is scanning tunneling microscopy, STM, which allows researchers to visualize individual atoms on surfaces. By exploiting the phenomenon of quantum tunneling, STM utilizes a sharp metal tip to scan over conductive materials, generating images that reveal the precise atomic arrangement of materials. This method has opened the door to studying materials previously beyond our reach, offering a window into the atomic level structure of various substances. Another important advancement is transmission electron microscopy, TEM, a technique that uses a beam of electrons transmitted through a thin specimen. As these electrons interact with the atoms in the sample, they generate detailed images of the material's atomic structure, allowing scientists to probe both the physical arrangement and the electronic properties of materials. This powerful technique has been especially crucial in advancing our understanding of semiconductors and metals, playing a central role in technological progress in electronics and materials science. Additionally, the field of atomic visualization has benefited from innovations in X-ray imaging, particularly with the advent of X-ray free electron lasers, XFELs. These powerful sources of X-rays generate ultra-fast pulses capable of capturing atomic movements in real time. By observing the rapid movements of atoms during chemical reactions, XFELs have opened new possibilities for studying dynamic systems and advancing material science. This level of observation is revolutionizing our approach to chemistry, material synthesis, and even biological research, offering the potential to design better materials, enhance energy storage systems, and develop groundbreaking new devices. As scientists continue to refine these atomic imaging techniques, the implications for technology and society are profound. By unveiling the atomic landscape, these innovations are driving progress in fields ranging from electronics to energy production. For example, the ability to observe the atomic structure of materials has already led to breakthroughs in the design of more efficient batteries and renewable energy solutions. In parallel, advancements in nuclear fusion and fission research have become closely intertwined with our deepening understanding of atomic interactions. Nuclear fusion, the process that powers the stars, occurs when light atomic nuclei combine to form a heavier nucleus, releasing vast amounts of energy. Understanding the behavior of protons, neutrons, and other atomic particles is key to harnessing fusion for practical energy production on Earth. Scientists are working tirelessly to replicate the extreme conditions of a star's core, where high temperatures and pressures enable fusion to take place. Success in this area could potentially offer a nearly limitless and clean source of energy for the planet. In contrast, fission involves the splitting of heavy atomic nuclei, such as uranium-235 or plutonium-239, into smaller fragments, releasing energy. This process is the basis for current nuclear power plants, which have been instrumental in generating electricity for much of the world. However, ongoing research into atomic structure has revealed ways to improve the efficiency and safety of fission reactions. By understanding the isotopes that are optimal for fission, scientists have been able to enhance reactor designs and safety protocols, contributing to the sustainability and reliability of nuclear power. Both fusion and fission research are dependent on advancements in particle physics, materials science, and plasma physics. Instruments like particle accelerators and spectrometers are indispensable tools in the study of atomic interactions, helping researchers understand the fundamental forces at play in both processes. With continued breakthroughs in these areas, the future of energy generation looks increasingly promising, with the potential for cleaner, more efficient power sources on the horizon. In conclusion, the exploration of atomic structure, particle physics, and atomic visualization techniques is not just a quest for theoretical knowledge, but a catalyst for technological progress. The deep understanding gained from these fields is transforming a wide array of industries, from medicine to energy production, reshaping the way we live and interact with the world around us. As these scientific endeavors push the boundaries of what we know, they continue to open new frontiers of possibility, offering hope for a future built on innovation and discovery. In the quest to understand and harness the forces that govern atomic behavior, the potential to transform the global energy landscape becomes increasingly clear. The fundamental study of how atoms bond and split is central to unlocking the future of energy solutions. This intersection of physics, chemistry, and engineering underscores the importance of basic research in atomic studies, as it is here that groundbreaking innovations begin to take shape. These innovations could eventually revolutionize our energy systems, leading to cleaner, more efficient sources of power. As scientists probe deeper into the mysteries of the atomic world, one area that holds remarkable promise is nuclear fusion. This process, which powers the sun and stars, has long been regarded as a potentially limitless, clean energy source. By fusing light atomic nuclei, typically isotopes of hydrogen, under extreme conditions of heat and pressure, vast amounts of energy are released. In such environments, the positively charged nuclei overcome their natural repulsion, allowing the strong nuclear force to bind them together, producing energy as a byproduct. If we can replicate these conditions on Earth, fusion could provide an abundant source of power without the harmful waste products associated with current nuclear fission technologies. On the other hand, nuclear fission, which is already utilized in nuclear reactors worldwide, operates through a different mechanism. In fission, the nucleus of a heavy atom, such as uranium or plutonium, is split into smaller nuclei, releasing a significant amount of energy, along with neutrons that can trigger further fission reactions. This chain reaction is the basis for modern nuclear power plants, which generate large amounts of energy from relatively small amounts of fuel. Fission, however, comes with significant concerns, including the handling of radioactive waste and the potential for catastrophic accidents. Despite these challenges, nuclear fission remains a key player in the global energy grid. Yet, the potential of fusion to provide a clean, sustainable energy source has driven scientists to relentlessly pursue breakthroughs in the field. If achieved, fusion could transform our energy systems, replacing fossil fuels and eliminating the risks associated with fission. The ongoing research in this area is not only crucial for energy production, but also for advancing our understanding of fundamental physics. As we delve deeper into the atomic interactions that make nuclear reactions possible, we are uncovering new ways to manipulate matter at its most fundamental level. At the same time, advancements in quantum technologies are opening new doors for atomic research. Quantum computers, which operate on the strange and counterintuitive principles of quantum mechanics, hold the potential to revolutionize our ability to simulate atomic interactions with unprecedented precision. By exploiting phenomena such as quantum entanglement and superposition, quantum computing could unlock new atomic behaviors and interactions that were previously beyond our reach. In parallel, quantum sensors, which rely on the same principles, could offer unprecedented sensitivity in measuring atomic properties, allowing for more accurate and detailed observations than ever before. Moreover, the exploration of ultra-cold atoms presents another exciting frontier in atomic physics. By cooling atoms to just above absolute zero, scientists can observe quantum phenomena on a macroscopic scale, offering new insights into the behavior of matter at the atomic level. This research not only allows scientists to replicate conditions similar to those in the early universe, but also sheds light on the fundamental forces that govern atomic interactions. Experiments with novel states of matter, such as Bose-Einstein condensates and fermionic superfluids, are already revealing unexpected properties that challenge our current understanding of the physical world. As technology continues to advance, new imaging techniques are enabling scientists to visualize atomic structures and dynamics with unprecedented clarity. Tools such as atomic force microscopy and advanced electron microscopy allow researchers to observe atomic-level interactions in real time, providing valuable insights into how atoms respond to external stimuli, such as electromagnetic fields and temperature fluctuations. These observations could refine existing theories and lead to the discovery of entirely new atomic behaviors, potentially reshaping our understanding of how matter behaves. In addition to these exciting developments, the study of atomic interactions with electromagnetic and gravitational fields holds significant promise for advancing theoretical physics. Understanding how atoms behave under the influence of these forces could offer crucial insights into the unification of the fundamental forces of nature, a long-sought goal in modern physics. By probing the ways in which atoms interact with fields, scientists may uncover new phenomena that challenge the boundaries of current theories, bringing us closer to a deeper understanding of the universe. These diverse avenues of research, the quest for nuclear fusion, the development of quantum technologies, the exploration of ultra-cold atoms, and advancements in imaging techniques, represent only a fraction of the potential that atomic physics holds. As scientists continue to push the limits of what we know, their discoveries will not only transform our energy systems, but also deepen our understanding of the very fabric of reality itself. In essence, the study of atomic interactions is not just an academic pursuit. It is a key to solving some of the most pressing challenges facing humanity. By unlocking the secrets of atomic behavior, we are laying the foundation for a future where energy is abundant, clean, and sustainable. Whether through the harnessing of nuclear fusion, the development of quantum technologies, or the refinement of existing energy systems, the advances made in atomic physics today are shaping the energy solutions of tomorrow. The possibilities are vast, and as research continues to progress, the path toward a cleaner, more efficient energy future becomes ever more attainable. At the most basic level, atoms are the core building blocks that underpin all matter in the universe. Every element, molecule, and compound is composed of atoms, making them fundamental not just to our daily existence, but also to the progress of technology and energy. These minute particles are the unsung heroes that make renewable energy systems work, enabling the transition to cleaner, more sustainable energy sources. The atomic structure of materials, whether it's a solar panel, a wind turbine, or a bioenergy source, determines how efficiently we can capture, convert, and store energy. Without understanding the atomic behavior within these systems, we would not be able to design and improve the green technologies that are essential for combating climate change. In the field of renewable energy, atoms play a particularly crucial role in how energy is captured and stored. Take solar panels, for example. The technology behind photovoltaic cells, used to convert sunlight into electricity, relies heavily on the atomic behavior of semiconductors like silicon. When sunlight strikes these materials, it excites the electrons within the silicon atoms, giving them enough energy to break free and create an electric current. This interaction between light and matter is the foundation of solar power, with the atomic arrangement of the semiconductor materials directly influencing how much energy can be generated. Similarly, in wind energy technologies, the design and performance of wind turbines depend on the atomic properties of the materials used to build them. From the blades to the support structures, every material is chosen for its atomic properties: strength, weight, and resistance to wear and tear from environmental factors. The atomic structure of metals, for example, affects their fatigue resistance, which is critical for the long-term operation of wind turbines under variable weather conditions. The stronger and more stable these atomic bonds are, the better the turbines can withstand the stresses they endure over time. When it comes to bioenergy, the atomic composition of organic matter plays a vital role in transforming biomass into usable fuel. Biomass is composed of a variety of molecules held together by atomic bonds, and when it is converted into biofuels, these bonds are broken and reformed to release energy-rich compounds. By understanding the molecular structure of different types of biomass, scientists can refine the conversion processes, making them more efficient and sustainable. This atomic knowledge is key to developing bioenergy technologies that can provide a renewable and carbon-neutral alternative to fossil fuels. The role of atoms also extends to energy storage, particularly in batteries, which are essential for storing the electricity generated by solar, wind, and other renewable energy sources. Lithium-ion batteries, for example, rely on the movement of lithium ions between the electrodes, which are atoms interacting at the most fundamental level. The efficiency and capacity of these batteries depend on how the atoms in the electrodes and electrolyte interact with each other. Understanding the behavior of atoms in these systems is crucial for improving battery technology, increasing energy density, and ensuring that renewable energy can be stored for later use. Ultimately, advancements in energy storage, bioenergy, solar power, and wind technology are driven by research into atomic interactions in various materials. These fundamental particles govern how energy is captured, transformed, and stored. Without a deeper understanding of atomic science, we would not have the efficient, sustainable technologies we rely on today, and future innovations would be impossible. Atoms are at the heart of the renewable energy revolution, quietly shaping the technologies that will power our world for generations to come. The atom, a journey through time and space. Everything around us, whether it's the stars above or the earth beneath our feet, is made of atoms. These tiny, almost invisible particles form the very fabric of existence. But what exactly is an atom, and where did it come from? How did these seemingly insignificant structures evolve into the diverse and complex forms of matter we observe in the universe today? To answer these questions, we must delve into the intriguing world of atoms, tracing their origins, their evolution, and their mysterious role in the universe. An atom is the smallest unit of matter, a fundamental building block that composes all substances in existence. Each atom consists of three primary components: protons, neutrons, and electrons. Protons and neutrons form the dense nucleus at the center of the atom, while electrons orbit around this nucleus at specific energy levels. Protons carry a positive charge, and the number of protons determines the type of element an atom represents. For example, a hydrogen atom has 1 proton, while a carbon atom has 6. Neutrons, on the other hand, have no charge, but they contribute to the mass of the atom. The number of neutrons can vary within atoms of the same element, resulting in different isotopes. Electrons, the smallest of the 3 subatomic particles, carry a negative charge and orbit the nucleus in defined regions known as electron shells. Despite being much lighter than protons and neutrons, electrons are responsible for the chemical properties of an atom. Their arrangement in the various shells determines how an atom will react with others and form bonds. The outermost electrons, known as valence electrons, are the most important in chemical bonding because they are the ones that interact with the electrons of other atoms. Understanding the structure of an atom is essential for the study of chemistry and physics. It provides a window into the behavior of matter and the way atoms interact with one another to form molecules and compounds. This atomic framework is the foundation of not only our everyday experiences, but also the complex workings of the universe itself. At the subatomic level, protons, neutrons, and electrons are made up of even more fundamental particles known as quarks. These tiny particles are held together by the strong nuclear force, which is one of the 4 fundamental forces in nature. Quarks come in different types or flavors and are bound together by particles called gluons, which act like glue, holding the quarks tightly within protons and neutrons. Protons consist of 2 up quarks and 1 down quark, while neutrons consist of one up quark and two down quarks. The combination of these quarks gives protons their positive charge and neutrons their neutrality. Interestingly, quarks themselves carry fractional electric charges. For example, an up quark has a charge of 2/3, while a down quark carries a charge of 1/3. When combined, these fractional charges result in the overall charge of protons and neutrons. However, the mass of protons and neutrons is not solely due to the quarks themselves, but is primarily a result of the energy associated with the strong force that binds the quarks together. This is a fascinating concept in physics, where mass and energy are intertwined, as famously described by Einstein's equation, E equals mc2. Quarks are a vital part of understanding the nature of matter itself. As the fundamental components of atomic nuclei, they determine the behavior of atoms and influence the stability of matter. The interactions of quarks, protons, and neutrons are what give rise to the chemical reactions that drive the vast array of processes in the universe, from the formation of stars to the energy production in nuclear reactors. In conclusion, atoms and their subatomic components, protons, neutrons, electrons, and quarks, are at the heart of everything in the universe. Their interactions shape not only the material world around us, but also the technological advances that fuel our future. From renewable energy systems to the most fundamental questions about the origins of matter, atoms remain the unsung architects of the universe, guiding the transformation of energy and matter across time and space. At the most fundamental level of the universe, there lies a vast and intricate network of tiny particles, each playing an essential role in shaping the reality we experience. Through the careful study of these particles and their interactions, scientists have unlocked and continue to uncover the deep mysteries of our cosmos. This journey to understand the very fabric of existence begins with atoms, the basic building blocks of matter. Every element on the periodic table is distinguished by its unique atomic structure, which directly determines its chemical and physical properties. At the heart of every atom lies a nucleus, made up of protons and neutrons. Protons carry a positive charge, while neutrons, as their name suggests, are electrically neutral. The number of protons in the nucleus is called the atomic number, and this number defines the element. For instance, hydrogen has just one proton, while carbon contains 6. Surrounding the nucleus are electrons, which have a negative charge. These electrons are arranged in distinct energy levels or shells, and their arrangement plays a crucial role in the behavior of the element, especially in chemical bonding and reactivity. As we move across the periodic table, the number of protons in each atom increases, and with it, the positive charge in the nucleus becomes stronger. This stronger positive charge pulls the electrons closer to the nucleus, affecting their energy levels and influencing the element's chemical and physical characteristics. As a result, metals tend to become more reactive as we move down a group in the periodic table, while nonmetals usually become less reactive. This process also involves the concept of isotopes, atoms of the same element that differ in the number of neutrons. These variations can affect the stability of the atom and lead to differences in properties like density or nuclear behavior. One of the most profound advances in atomic theory came with the electron cloud model, which revolutionized our understanding of atomic structure. The earlier Bohr model had depicted electrons as fixed in specific orbits, but the electron cloud model offered a more complex, probabilistic view. According to quantum mechanics, electrons do not follow strict paths. Instead, they exist in regions around the nucleus, and the probability of finding an electron in any particular location is governed by a cloud. This model acknowledges the uncertainty in the exact position of an electron at any given time, a concept known as Heisenberg's uncertainty principle. In this cloud model, the density of the cloud indicates the likelihood of finding an electron in a certain region. Areas of higher density correspond to higher probabilities of electron presence. This new understanding of atomic behavior reflects the dual nature of particles, where electrons behave both as particles and as waves. Such a model has been instrumental in explaining chemical bonding, as it demonstrates how electrons interact between atoms to form molecules. The arrangement of electrons dictates which atoms can bond and what type of bonds they will form, whether covalent or ionic, influencing how chemical reactions occur. The electron cloud model has also paved the way for significant advancements in various fields. By understanding how atoms and their electrons behave, scientists can manipulate chemical reactions in fields such as materials science, electronics, and even medicine. The model has become a critical tool in exploring the universe at the smallest scales, continuing to guide research and innovation. The journey to understanding the atom is not just a modern phenomenon. It traces its roots to ancient Greece. Around 450 BCE, the philosopher Democritus first proposed that everything in the universe was made of tiny, indivisible particles, which he called atomos, meaning uncuttable. Though his ideas were largely philosophical and lacked experimental evidence, they sparked the curiosity that would eventually lead to the development of atomic theory. Fast forward to the early 19th century, and the English chemist John Dalton formulated the first modern atomic theory. Dalton reintroduced the idea of atoms, asserting that each element consisted of identical atoms, each with a specific weight and set of properties. His work involved meticulous quantitative experiments that demonstrated that chemical reactions involve the rearrangement of atoms to form compounds. Dalton's atomic theory provided the framework for future scientists to build upon and refine. Later, in the late 19th century, J.J. Thomson made an unprecedented discovery: the electron. Through his experiments with cathode rays, Thomson demonstrated that atoms were not indivisible as once believed. He introduced the plum pudding model, which suggested that the atoms were made up of electrons embedded in a positively charged soup. This discovery was pivotal in changing our understanding of the atomic structure and opened the door for further exploration. At the dawn of the 20th century, Ernest Rutherford made another breakthrough. His Goyle experiment revealed that atoms have a tiny, dense nucleus at their core, surrounded by orbiting electrons. This led to the development of the nuclear model of the atom, in which protons and neutrons form the nucleus, while electrons orbit in the surrounding space. Rutherford's discovery reshaped our understanding of atomic structure, laying the foundation for future developments in quantum mechanics. Collectively, these discoveries represent a transformative period in our understanding of matter. From the ancient musings of Democritus to the groundbreaking insights of modern scientists, the evolution of atomic theory has reshaped the way we view the world. Today, our knowledge of atomic structure is essential not only in chemistry, but also in many other scientific disciplines. As we look ahead, we continue to explore the complex behavior of particles guided by the principles established by these early pioneers. Our understanding of the atom, once limited to speculative philosophy, has grown into a powerful tool for innovation, unlocking the secrets of the universe on the smallest scales. The study of atomic and subatomic particles remains an ever-evolving frontier in science, an ongoing journey that stretches the limits of human knowledge and imagination. The journey to understanding the atomic structure is a fascinating saga that spans centuries, involving ancient philosophical musings, radical scientific revolutions, and breakthroughs in experimental techniques. This quest, which began long before the advent of modern science, has evolved into a rich, intricate framework that has redefined our perception of the universe at its most fundamental level. In the beginning, the concept of the atom was born from philosophical speculation. The ancient Greeks, most notably Leucippus and Democritus, introduced the idea of the atom as an indivisible particle that made up all matter. However, their ideas lacked empirical support, and over time they were overshadowed by Aristotelian philosophy, which dominated for centuries. This philosophy proposed a more qualitative understanding of the world, focusing on elements like earth, water, air, and fire as the fundamental building blocks of matter. Fast forward to the 17th century, when the scientific method began to emerge as a structured approach to inquiry. Pioneers like Robert Boyle and John Dalton reignited the idea of atoms, bringing it back to the forefront of scientific discussion, but this time with an experimental edge. Boyle's work in chemistry and Dalton's atomic theory laid the foundation for the modern understanding of atoms, moving away from speculation to a more empirical and rigorous approach. In the early 19th century, Dalton's groundbreaking theory posited that matter is composed of atoms that are indivisible and indestructible. He noted that atoms of different elements have different weights, setting the stage for a deeper understanding of chemical reactions. Dalton's model, although simple, was instrumental in shifting scientific thought toward the idea that atoms were not only real, but crucial to explaining the behavior of matter. However, as scientific research advanced, new discoveries forced a rethinking of the atom. In the late 19th century, the famous British physicist J.J. Thomson conducted a series of experiments with cathode rays. His findings led to the discovery of the electron, a fundamental subatomic particle with a negative charge. With this revelation, Thomson proposed the plum pudding model of the atom, which depicted the atom as a sphere of positive charge with electrons scattered throughout like plums in a pudding. This model was a pivotal moment in atomic theory, but it did not last long. The emerging experimental evidence would soon challenge this view and give birth to a new understanding of the atom. In the early 20th century, the world of atomic science underwent a dramatic transformation, thanks to the work of scientists like Ernest Rutherford. Rutherford's gold foil experiment in 1912 was a turning point. By bombarding a thin sheet of gold with alpha particles, he observed that while most of the particles passed straight through, a small number were deflected at large angles. This unexpected result led to the realization that the atom was not a diffuse, indivisible mass, as previously thought, but rather had a small, dense nucleus at its center containing most of its mass, with electrons orbiting around it. Rutherford's findings dismantled the plum pudding model and marked the dawn of a new atomic model. Building on Rutherford's work, Niels Bohr took the next step in refining the atomic model. In 1913, he proposed that electrons move in fixed orbits, or energy levels, around the nucleus, much like planets orbiting the sun. Bohr's model not only provided a more accurate description of atomic structure, but also explained the spectrum of hydrogen, showing how electrons could jump between orbits, absorbing or emitting energy in the form of light. This was the first integration of quantum principles into the understanding of atomic behavior. The 20th century continued to bring new revelations about the atom. In 1932, James Chadwick discovered the neutron, a neutral subatomic particle located in the nucleus. The neutron's discovery added a new layer of complexity to the atomic model, as it revealed that the nucleus was made up of both protons and neutrons, not just protons. This finding led to the realization that atoms of the same element could exist in different forms, now known as isotopes. Isotopes have the same number of protons but differ in the number of neutrons, giving them different atomic masses but similar chemical properties. The discovery of isotopes was a game changer, altering the way scientists viewed atomic structure. Before isotopes were understood, it was assumed that all atoms of an element were identical in both structure and mass. However, the identification of isotopes showed that atomic mass could vary within elements, challenging long-held assumptions. For example, carbon primarily exists as carbon-12, but it also has isotopes such as carbon-13 and carbon-14, which are crucial in fields like radiocarbon dating. The realization that isotopes could exist also had profound implications for numerous scientific disciplines. In nuclear physics, isotopes became fundamental in understanding nuclear reactions and radiation. In medicine, isotopes have found practical applications in radiation therapy and diagnostic techniques, allowing for the treatment and detection of diseases like cancer. Moreover, isotopes have become invaluable tools in biochemical research and archaeological studies, where they are used as tracers in experiments and, to date, ancient artifacts. The discovery of neutrons and isotopes set the stage for the development of quantum mechanics, which further refined our understanding of atomic behavior. Quantum mechanics introduced the concept of wave functions, which describe the probability of finding an electron in a given region rather than defining its exact position. This was a departure from the previous models that depicted electrons as particles in fixed orbits. Instead, electrons are now understood as existing in a cloud of probabilities, their exact location and momentum inherently uncertain. This new perspective, known as the quantum mechanical model of the atom, has been crucial in shaping modern atomic theory. Today, our understanding of the atom is far more sophisticated than ever before. The atom is no longer seen as a simple, indivisible particle, but rather a complex structure consisting of protons, neutrons, and electrons, with each particle playing a vital role in the atom's overall behavior. Additionally, the exploration of quantum mechanics continues to reveal the atom's intricate nature, with ongoing research into quantum states, entanglement, and the interactions of subatomic particles. This progression, from philosophical musings about indivisible particles to the highly refined quantum mechanical model of the atom, demonstrates the profound evolution of scientific thought. What began as an ancient Greek idea has, through centuries of inquiry and experimentation, blossomed into a framework that not only explains the structure of matter, but also informs numerous fields, from chemistry and physics to medicine and engineering. As our understanding of atomic theory continues to evolve, one thing remains clear. The journey of scientific discovery is far from over. The atom, once thought to be the fundamental building block of matter, is now understood to be a window into the deeper mysteries of the universe. What started as an abstract concept in ancient philosophy has become a cornerstone of modern science, guiding our exploration of everything from the smallest particles to the vastness of space itself. Atomic theory, as we know it today, is the result of centuries of evolving thought and rigorous scientific investigation. The discovery of the atom's true nature revolutionized not only our understanding of matter, but also catalyzed an era of unprecedented exploration into the forces that govern the universe. This new perspective on atomic theory opened the doors to deep inquiries into the forces that influence atomic stability and nuclear reactions. The exploration of isotopes, those variants of elements with the same number of protons but differing numbers of neutrons, further advanced our understanding. Through isotopes, scientists began to investigate nuclear fission and fusion in greater detail, processes that power the stars and fuel the creation of the elements we find scattered throughout the cosmos. The implications of isotopes are far-reaching, impacting diverse scientific disciplines, from chemistry to astronomy. Their study enhances our comprehension of the natural world, offering insights that extend across realms as disparate as medicine, geology, and astrophysics. One of the pivotal breakthroughs in atomic research came with the invention of the electron microscope. This revolutionary tool dramatically changed the landscape of scientific inquiry by providing a way to observe structures at an atomic scale, something previously unimaginable. Unlike traditional light microscopes, which are limited by the wavelengths of visible light, the electron microscope uses beams of electrons, particles with much shorter wavelengths. This innovation unlocked the ability to examine structures at an unprecedented level of detail, revealing features that had long been hidden from view. The electron microscope allowed scientists to peer into the microscopic world, making the once impossible task of observing atomic structures a reality. This tool helped uncover the complexities of materials at their most fundamental level, revealing atomic arrangements within materials and offering insights into crystalline structures, defects, and the behavior of individual atoms. By visualizing these minute details, researchers began to see the connections between atomic structure and material properties. Understanding how atoms bond and interact led to breakthroughs in numerous fields, including nanotechnology, material science, and semiconductor research. These discoveries have shaped the technological landscape of our modern world, enabling innovations that were once thought to be beyond our reach. Moreover, the electron microscope opened new possibilities for studying dynamic processes occurring at the atomic level. Scientists could now observe chemical reactions and phase changes in real time, watching phenomena unfold before their eyes rather than relying on theoretical models alone. This empirical evidence has proven transformative for both chemistry and physics, providing profound insights into material properties and the fundamental principles governing the natural world. The advent of the electron microscope thus created a gateway for deeper exploration into the atomic realm, empowering researchers to challenge and refine existing theories and contribute to the ongoing evolution of scientific knowledge. As science continued to push the boundaries of understanding, the phenomenon of nucleosynthesis emerged as another critical piece in the puzzle of the universe's origins. Nucleosynthesis is the process by which elements are formed through nuclear reactions, predominantly occurring within stars. At the heart of a star, conditions of extreme temperature and pressure create the perfect environment for these reactions to take place. Hydrogen, the simplest and most abundant element in the universe, acts as the fundamental building block. Through nuclear fusion, hydrogen nuclei combine to form helium, releasing a tremendous amount of energy in the process. This energy is the source of the light and heat emitted by stars, and it plays a crucial role in sustaining life on Earth. Over time, as stars evolve and exhaust their hydrogen fuel, they engage in more complex fusion reactions, giving rise to heavier elements, elements that make up the very building blocks of planets, life, and the universe as we know it. At the core of all matter lies the atom, an astonishingly small yet infinitely complex structure that serves as the foundation of everything in existence. From the stars in the heavens to the particles that make up the earth beneath our feet, everything is built from atoms. Yet the question remains, what exactly is an atom? How did these minuscule structures come into being, and what role do they play in the grand design of the universe? To answer these questions, we must first explore the nature of the atom itself. An atom is the smallest unit of matter that retains the properties of an element. Each atom consists of three primary subatomic particles: protons, neutrons, and electrons. Protons and neutrons are located at the atom's center in the nucleus, while electrons orbit around the nucleus in defined energy levels or shells. Protons carry a positive charge, and the number of protons within an atom determines the element's identity. For example, hydrogen has just one proton, while carbon has 6. Neutrons, which have no charge, contribute to the mass of the atom. Interestingly, the number of neutrons can vary among atoms of the same element, leading to the creation of isotopes. Electrons, by contrast, are much smaller than protons or neutrons, and they carry a negative charge. It is these electrons that play a pivotal role in the chemical behavior of atoms, as they interact with other atoms to form bonds. The way electrons are arranged in their respective shells determines an atom's chemical reactivity and its ability to form different types of molecules and compounds. The outermost electrons, called valence electrons, are especially important because they are directly involved in chemical reactions. Understanding the structure of the atom is essential not just for chemistry, but for physics as well, as it offers critical insights into how matter interacts and transforms on a fundamental level. At a deeper level, atoms themselves are composed of even more fundamental particles: protons, neutrons, and electrons. Protons and neutrons reside in the nucleus and are held together by the strong nuclear force, one of the 4 fundamental forces of nature. The strong force binds protons and neutrons tightly within the nucleus, overcoming the repulsion between the positively charged protons. Electrons, on the other hand, are lighter particles that orbit the nucleus in defined regions known as orbitals. The electromagnetic force between the protons and electrons keeps the atom stable, maintaining a balance between the opposing charges. Interestingly, the behavior of matter is determined not only by the interactions between protons, neutrons, and electrons, but also by the quarks that make up protons and neutrons. Quarks are elementary particles that combine in specific ways to form protons and neutrons. Protons consist of 2 up quarks and 1 down quark, while neutrons are composed of 1 up quark and 2 down quarks. These quarks carry fractional electric charges. Up quarks have a charge of 2/3, while down quarks carry a charge of -1/3. The interactions between quarks, mediated by particles called gluons, provide the necessary binding force that holds protons and neutrons together within the nucleus. It is important to note that most of the mass of protons and neutrons does not come from the quarks themselves, but rather from the energy associated with the strong nuclear force that binds them together. This energy is described by Einstein's famous equation, E=mc², which shows that energy and mass are interchangeable. Gluons, though massless, play a significant role in the overall mass of protons and neutrons by mediating the strong force that holds the quarks together. Thus, the very fabric of matter is built from these fundamental particles, and understanding their properties is crucial for unlocking the mysteries of the universe itself. By delving into the structure of atoms and the particles that compose them, we uncover the very essence of matter and the forces that govern its behavior. These insights not only illuminate the intricate workings of the natural world, but also pave the way for future discoveries that will continue to shape our understanding of the universe. From the formation of elements in stars to the creation of novel materials at the atomic scale, the study of atoms and subatomic particles remains a cornerstone of scientific inquiry, one that holds the key to unlocking the deepest secrets of the cosmos. Scientists have long been on a quest to understand the universe at its most fundamental level, unlocking the mysteries of the cosmos by investigating the tiniest building blocks of matter. These microscopic particles, atoms, and their interactions govern the chemical and physical properties of everything around us. At the heart of this exploration lies the study of atoms, each of which holds the key to the behaviors and characteristics of the elements that make up the universe. Every element on the periodic table is defined by a unique atomic structure. This structure is determined by the arrangement of particles within the atom: protons, neutrons, and electrons. The protons, which carry a positive charge, and the neutrons, which are neutral, come together to form the atom's nucleus. The number of protons in the nucleus, known as the atomic number, is what determines the element itself. For example, hydrogen, the simplest element, has 1 proton in its nucleus, while carbon, an essential element for life, has 6. Orbiting the nucleus are electrons, which carry a negative charge. These electrons are arranged in distinct energy levels, or electron shells, around the nucleus. The way electrons are arranged and interact plays a critical role in chemical bonding and reactivity, which are the foundations of all chemical processes. Elements can be grouped into categories based on their electron configurations. Some of the most notable groups are the noble gases, alkaline metals, and halogens. Each of these groups exhibits distinct behaviors due to the way their atoms are arranged. As we move across the periodic table, the number of protons in the nucleus increases, resulting in a larger positive charge in the nucleus. This stronger positive charge pulls electrons closer to the nucleus, affecting the electron's energy levels. As a result, the chemical and physical properties of the elements also change. Metals, for example, tend to become more reactive as you move down a group, while nonmetals typically become less reactive. Additionally, the atomic structure can vary between isotopes, which are atoms of the same element that differ in the number of neutrons they contain. These variations in neutron count can significantly influence an atom's stability and physical properties, including its density and behavior during nuclear reactions. By examining these atomic structures, scientists can gain valuable insights into the behaviors of elements in chemical reactions and natural cycles. This understanding is crucial to revealing the complexity of the material world we live in. One of the most groundbreaking developments in atomic theory came with the electron cloud model, which revolutionized our understanding of atomic structure. Unlike the earlier Bohr model, which depicted electrons as fixed in defined orbits around the nucleus, the electron cloud model presented a more sophisticated view. It suggested that electrons do not occupy fixed paths, but rather exist in a cloud of probability surrounding the nucleus. This concept is rooted in quantum mechanics, which posits that particles like electrons exhibit both wave-like and particle-like properties. Rather than being confined to specific orbits, electrons occupy regions of space defined by probabilities. These regions, often referred to as orbitals, have varying densities that represent the likelihood of finding an electron at any given moment. Areas with a denser cloud indicate a higher probability of locating an electron, while areas with a sparser cloud suggest a lower likelihood. This model allows scientists to more accurately predict atomic behavior by acknowledging the uncertainty and variability of electron positions. The electron cloud model is instrumental in explaining chemical bonding and reactions. The way electrons are arranged and behave in different atoms determines how they interact with each other to form molecules. This is crucial to understanding the nature of chemical bonds, whether covalent, ionic, or metallic. By studying these interactions, chemists are able to predict and manipulate chemical reactions in a wide array of practical applications, from developing new materials to advancing pharmaceuticals. Ultimately, the electron cloud model not only enhances our understanding of atomic behavior, but it also opens new pathways for advancements in various fields, such as materials science, electronics, and even medicine. With the advent of increasingly sophisticated tools and techniques, our ability to study and manipulate the atomic world continues to expand, enabling innovations that were once thought impossible. As we delve deeper into the intricacies of atomic interactions, the electron cloud model remains a cornerstone of modern science, guiding our exploration of the universe at its most microscopic scale. The development of atomic theory is a captivating journey, one that has been shaped by the contributions of many brilliant minds throughout history. From the early ideas of ancient philosophers to the groundbreaking work of scientists in the 20th century, each step in the evolution of atomic theory has brought us closer to understanding the nature of the universe itself. The groundwork laid by these pioneers continues to influence and inspire scientific discoveries to this day, paving the way for future generations of researchers to further explore the secrets of the atom. In the history of science, the search to understand the nature of matter has been an ongoing journey, one that has evolved from early philosophical musings to groundbreaking experimental discoveries. It all began in ancient Greece around 450 BCE with the philosopher Democritus, who first proposed the revolutionary idea that everything in the universe was composed of tiny, indivisible particles. He called these particles atomos, which translates to uncuttable. Democritus's vision was bold. He suggested that all matter, from the smallest pebble to the vast expanses of the cosmos, was made up of these fundamental units. However, despite the elegance of his idea, Democritus lacked the tools and empirical evidence to prove his theory, and as such, it was relegated to the realm of philosophy, largely overshadowed by the more dominant Aristotelian ideas. Aristotle's worldview emphasized matter as a continuous substance, composed of four basic elements: earth, air, fire, and water. For centuries, the atomistic concept would remain largely forgotten, but the spark ignited by Democritus would not be easily extinguished. As the centuries rolled on, particularly by the 17th century, a new intellectual movement began to take shape. The scientific method gained prominence, and thinkers began to apply observation, experimentation, and reason to questions about the nature of matter. It was in this climate that, in the early 19th century, English chemist John Dalton would revisit and refine the concept of the atom. Dalton is credited with formulating the first modern atomic theory. Through his meticulous experiments, Dalton proposed that each element is composed of atoms that are identical in weight and properties but differ from atoms of other elements. This marked a significant shift, not only in the understanding of atomic structure, but also in the approach to scientific inquiry. Dalton's atomic theory was grounded in quantitative experiments that demonstrated that atoms are neither created nor destroyed in chemical reactions, but are instead rearranged to form new compounds. His work was instrumental in laying the foundation for the future study of chemical reactions and provided a systematic framework for subsequent discoveries in atomic science. It was this framework that allowed future scientists to build upon Dalton's ideas and delve deeper into the complexities of atomic behavior. The late 19th century saw another dramatic leap in atomic theory, thanks to the work of J.J. Thomson. Building on earlier observations of cathode rays, Thomson conducted experiments that led to the discovery of the electron, a negatively charged subatomic particle. This finding shattered the long-standing belief that atoms were indivisible. Instead, Thomson introduced the plum pudding model, which suggested that atoms consisted of electrons embedded in a diffuse, positively charged substance. Though this model was eventually superseded, it marked a critical turning point in atomic theory, demonstrating that atoms were far more complex than previously imagined and setting the stage for future breakthroughs in the field. Yet, it was not until the early 20th century that atomic theory would be radically transformed. Ernest Rutherford, in 1911, conducted his now famous gold foil experiment, which would forever alter the understanding of atomic structure. By bombarding a thin sheet of gold with alpha particles, Rutherford discovered that atoms are not solid entities as previously thought, but are made up of a vast majority of empty space with a tiny, dense nucleus at the center. This nucleus contained positively charged protons and neutrally charged neutrons, while the electrons occupied the space around the nucleus. Rutherford's findings led to the development of the nuclear model of the atom, which painted a more accurate picture of atomic structure than the plum pudding model had. Rutherford's work was a monumental achievement, but it also left unanswered questions. One of the most pressing issues was the behavior of electrons in the atom. If electrons were orbiting the nucleus, as Rutherford's model suggested, why didn't they spiral inward due to the electromagnetic forces between the positive nucleus and the negative electrons? This conundrum would be addressed in the following decades by scientists such as Niels Bohr, who introduced the idea of quantized energy levels for electrons. These early 20th century discoveries set the stage for the development of quantum mechanics, a field that would revolutionize physics and our understanding of the subatomic world. The journey from Democritus's philosophical musings to the precise mathematical descriptions of atomic behavior was a process marked by relentless curiosity and the gradual accumulation of knowledge. The work of these scientists, from Democritus to Rutherford, helped shape the scientific landscape we know today. Their collective discoveries didn't just answer questions about the atom, they opened up new realms of inquiry, propelling humanity into an era of discovery that continues to this day. What began as a philosophical idea in ancient Greece evolved into one of the most profound and transformative scientific theories of all time. The exploration of the atom has become not only a cornerstone of modern science, but also a testament to the power of curiosity, experimentation, and the pursuit of knowledge. Today, the atom is no longer a mere theoretical construct, but a fundamental building block of all matter, continuing to inspire exploration at the frontier of quantum mechanics and beyond. Modern atomic theory is a testament to the profound evolution of scientific understanding. Over time, the atom, once seen as a simple, indivisible particle, has revealed itself to be a marvel of complexity, consisting of protons, neutrons, and electrons, all governed by the fascinating principles of quantum mechanics. The journey from ancient philosophy to the cutting-edge science of today showcases a gradual transformation of ideas, where initial speculations have evolved into an intricate framework that continues to shape our comprehension of matter and the cosmos. The quest to understand the atomic structure began centuries ago, but it was the early 20th century that marked a pivotal era in its development. One of the most significant breakthroughs in atomic theory came from Ernest Rutherford, whose famous gold foil experiment in 1909 dramatically altered the way scientists thought about atoms. Rutherford directed a stream of positively charged alpha particles at a thin sheet of gold foil, expecting the particles to pass through without significant deflection. To his surprise, while most alpha particles did indeed pass through, a small fraction bounced back at large angles. This unexpected result led to a groundbreaking revelation. Atoms are not solid, indivisible units, but contain vast regions of empty space with a dense nucleus at their center, which houses most of the atom's mass. Rutherford's discovery laid the foundation for a deeper exploration of atomic structure. Following this, Niels Bohr introduced a further refinement of the model in 1913. Bohr proposed that electrons, the subatomic particles that orbit the nucleus, travel in defined paths or orbits, similar to how planets orbit the sun. This idea not only brought clarity to the structure of the atom, but also helped explain the behavior of light. Bohr's model accounted for the emission and absorption spectra of hydrogen by suggesting that electrons could jump between these orbits, absorbing or emitting energy in the form of light. Bohr's work incorporated early quantum principles, signifying a crucial shift towards a new understanding of atomic behavior. However, the development of atomic theory didn't stop there. In 1932, James Chadwick's groundbreaking discovery of the neutron expanded the atomic model once again. By showing that the nucleus contained not only protons but also neutrons, Chadwick's work deepened our understanding of the atom's composition. Neutrons, which have no electric charge, contribute significantly to an atom's mass without influencing its charge. This revelation had far-reaching consequences, one of which was the realization that atoms of the same element could exist in different forms. These variations are known as isotopes. The concept of isotopes, introduced during the early 20th century by scientists like Frederick Soddy and J.J. Thomson, reshaped our understanding of atomic structure. Isotopes are atoms that share the same number of protons but differ in their number of neutrons, resulting in varying atomic masses. This discovery challenged the previously held belief that all atoms of an element were identical in both structure and mass. The recognition that elements could have different isotopic forms opened up new avenues for research and discovery across many scientific disciplines, from chemistry and physics to medicine and archaeology. For example, carbon primarily exists as carbon-12 with 6 protons and 6 neutrons, but it also exists in the forms of carbon-13 and carbon-14. These isotopes, while chemically identical, differ in their mass and certain physical properties. The existence of isotopes underscored the complexity of atomic structures and led to new ways of thinking about the universe's building blocks. The discovery of isotopes had profound applications in numerous fields, especially in nuclear physics and medicine. Isotopes are essential in radiation therapy, where specific isotopes are used to treat cancer, as well as in diagnostic techniques such as PET scans. In addition, isotopes are vital tools in biochemical research and archaeological studies, allowing scientists to trace the path of molecules in the body or date ancient artifacts through methods like radiocarbon dating. This practical significance of isotopes has helped bridge the gap between theoretical atomic science and real-world applications. Moreover, isotopes have deepened our exploration of nuclear reactions such as fission and fusion, processes that power stars and drive the creation of elements in the universe. By understanding how isotopes behave, scientists have gained insight into the forces that govern atomic stability and how these reactions can be harnessed for energy production both on Earth and in the vastness of space. As atomic theory evolved, another monumental leap occurred with the invention of the electron microscope in the 1930s. This tool revolutionized the study of the atomic world by allowing scientists to visualize structures at the atomic scale. Unlike traditional light microscopes, which are limited by the wavelength of visible light, the electron microscope uses beams of electrons with much shorter wavelengths, enabling it to observe much smaller structures in unprecedented detail. This technological breakthrough provided scientists with the ability to peer into the fundamental building blocks of matter, revealing the complex arrangements of atoms in materials. With the electron microscope, researchers could investigate the atomic structure of various materials and observe phenomena that were previously beyond the reach of scientific inquiry. The ability to visualize individual atoms and study their arrangement within a material opened new frontiers in several fields, including nanotechnology, material science, and semiconductor research. These advances in atomic imaging have been pivotal in shaping modern technologies, from the development of advanced computer chips to innovations in energy storage and material fabrication. The discoveries and advancements that have shaped our understanding of atomic theory have had far-reaching consequences, not just for science, but for society as a whole. The model of the atom, once a simple idea in the minds of ancient philosophers, has evolved into a sophisticated and dynamic framework that continues to guide our exploration of the universe. Today, the study of atomic and subatomic particles remains at the forefront of scientific research, with ongoing investigations into the quantum realm revealing even more about the strange and mysterious behavior of matter. From Rutherford's gold foil experiment to the discovery of isotopes and the invention of the electron microscope, the path toward understanding the atom is a testament to the power of human curiosity and ingenuity. As we continue to unlock the secrets of the atomic world, we are not only expanding our knowledge of matter, but also transforming the way we understand the very fabric of reality itself. The electron microscope has revolutionized our understanding of the microscopic world, offering scientists unprecedented access to the atomic realm. With its high-resolution imaging capabilities, it has unlocked new frontiers in scientific exploration, allowing researchers to observe and analyze processes at the atomic level in real time. This monumental tool has been instrumental in the study of chemical reactions, phase transitions, and the dynamic behaviors of materials, phenomena that were once relegated to theoretical models. Now scientists can witness these processes unfold before their eyes, marking a significant leap in our empirical understanding of nature. Before the advent of the electron microscope, The world of atoms and subatomic particles was largely hidden from view, confined to theoretical speculation. But with this breakthrough technology, a new era in scientific discovery was born. Researchers are no longer constrained to guesswork or indirect measurements. They can now study the intricate interactions between particles as they occur. This transformative tool has reshaped entire fields of chemistry and physics, providing critical insights into the properties of materials, the mechanisms of chemical reactions, and the forces that govern the behavior of matter at the most fundamental levels. The electron microscope represents a triumph of human ingenuity, a testament to our relentless pursuit of knowledge and understanding. By bridging the gap between the observable and the unseen, it allows us to peer into the very building blocks of the universe. It has enabled scientists to refine existing theories, challenge established norms, and uncover new truths about the nature of matter and energy. The discoveries made with the electron microscope continue to resonate across multiple disciplines, and its impact on science is profound and lasting. The pursuit of understanding doesn't stop at the atomic scale. One of the most fundamental processes in the universe, nucleosynthesis, takes place deep within stars. This is the process by which elements are formed through nuclear reactions, primarily within the cores of stars, and it is responsible for creating the building blocks of the universe itself. Within these stellar furnaces, extreme temperatures and pressures provide the ideal conditions for nuclear fusion to occur. At the core of a star, hydrogen, the most abundant and simplest element, undergoes fusion, merging into helium and releasing vast amounts of energy. This energy is what powers stars and creates the light we see in the night sky. As stars evolve, they deplete their hydrogen fuel, and more massive stars experience a fascinating transformation. Their cores contract and heat up, enabling the fusion of heavier elements like carbon and oxygen. This process continues, with each new stage of fusion producing increasingly heavier elements. From hydrogen and helium, elements such as carbon, nitrogen, and oxygen are formed, and eventually the core temperature becomes high enough to fuse elements all the way up to iron. However, the creation of elements beyond iron requires much more extreme conditions, particularly those created in supernovae, the explosive deaths of massive stars. When a star reaches the end of its life cycle, it may explode in a cataclysmic supernova, a violent event that sends shockwaves across the universe. These explosions are not only spectacular displays of cosmic energy, but they also create and disperse elements heavier than iron, such as gold, platinum, and uranium. The material ejected in these explosions enriches the interstellar medium, the vast expanse of gas and dust between stars. Over time, this enriched material can gather to form new stars, planets, and potentially even life itself. In this way, nucleosynthesis plays a vital role not only in the formation of the elements, but also in the ongoing evolution of the universe. The very fabric of the universe, its atoms, elements, and stars, is a product of an intricate and dynamic process that has been unfolding for billions of years. At the heart of this process is the Big Bang, the event that marks the beginning of the universe as we know it. Around 13.8 billion years ago, the universe began in an incredibly hot and dense state. In the moments following the Big Bang, the universe expanded rapidly, cooling as it did so. This cooling was crucial, for it set the stage for the formation of the first atoms. During the earliest moments after the Big Bang, conditions were ideal for nuclear fusion to take place. Protons and neutrons, the building blocks of atomic nuclei, formed from the hot, dense soup of particles that filled the universe. As the universe continued to expand and cool, these protons and neutrons collided and fused, creating the nuclei of the simplest elements, hydrogen and helium. In fact, approximately 75% of the matter in the universe became hydrogen, while around 25% became helium. This process, known as Big Bang nucleosynthesis, established the foundation for the more complex elements that would form later in stars. However, the formation of atoms didn't happen immediately. For several 100,000 years, the universe remained too hot for electrons to combine with nuclei, leaving the universe filled with a plasma of free particles. Eventually, as the universe continued to cool, the conditions became favorable for recombination. Electrons combined with atomic nuclei to form neutral atoms, primarily hydrogen and helium. This process allowed light to travel freely through space for the first time, and the photons released during recombination have been traveling ever since. This radiation is what we now detect as the cosmic microwave background, an essential remnant of the early universe. The formation of neutral atoms was just the beginning of the cosmic journey. As the universe continued to evolve, these atoms clumped together under the force of gravity, eventually forming the first stars and galaxies. Within these massive structures, nuclear fusion began in earnest, producing heavier elements and enriching the cosmos with the building blocks of planets and life. Over billions of years, this process led to the creation of the vast, complex universe we observe today, a universe filled with stars, planets, and galaxies, each a product of the ongoing cycle of nucleosynthesis. From the explosive birth of the universe to the quiet fusion of elements in the hearts of stars, the story of nucleosynthesis is one of transformation and renewal. It is a process that shapes not only the matter in the universe, but the very evolution of the cosmos itself. Through each cycle of star birth and death, elements are created, recycled, and transformed, contributing to the ever-expanding richness of the universe and the diverse array of matter that fills it. The ongoing process of nucleosynthesis is not only essential for the formation of atoms, but for the continued existence and development of the universe itself. The journey from the Big Bang to the creation of the first atoms is an awe-inspiring tale of transformation, a cosmic evolution that set the stage for the vast and intricate universe we now inhabit. This journey unfolds over billions of years, driven by extraordinary events and processes that shape the elements of the cosmos. It all begins in the aftermath of the Big Bang, where, in the blink of an eye, space itself rapidly expanded, and the universe cooled enough for fundamental particles to come together. This led to the formation of the first simple atoms, hydrogen and helium. However, the true complexity of the universe would take millions of years to unfold, and much of it would be written in the hearts of stars. The creation of elements heavier than hydrogen and helium, such as carbon, oxygen, and beyond, occurs primarily during the life cycles of stars. This process is known as stellar nucleosynthesis, and it plays a pivotal role in building the chemical structure of the universe. It all begins with nuclear fusion. Under extreme temperatures and pressures, lighter elements combine to form heavier ones. In the early stages of a star's life, this process starts with hydrogen nuclei fusing to form helium. This marks the star's place on the main sequence, where it remains stable for the majority of its life. But when a star exhausts its hydrogen fuel, this delicate balance of energy begins to falter. The star expands, and the temperatures rise once again, sparking the fusion of helium into even heavier elements, such as carbon and oxygen. This phase of stellar evolution sets the stage for the formation of even more complex elements. As the star ages and reaches the end of its life cycle, it begins a dramatic transformation. Massive stars, in particular, undergo a massive expansion, swelling into what we call red giants. During this expansion, nuclear fusion continues, but it takes on new dimensions. In these later stages of stellar life, fusion produces elements as heavy as iron through processes such as the triple alpha process. However, the creation of elements heavier than iron, such as gold and uranium, requires even more extreme conditions. It is in these moments of intense cosmic upheaval that the universe reveals its most explosive processes. The formation of these heaviest elements, those beyond iron, typically occurs in cataclysmic events like supernovae and the mergers of neutron stars. Supernovae, vast explosions marking the death of massive stars, release an unimaginable amount of energy, creating an environment ripe for rapid neutron capture, known as the R process. This process is essential for the creation of elements much heavier than iron. Through the energy released by these explosions, heavy elements like gold, platinum, and uranium are forged in the hearts of dying stars. Similarly, the collision of neutron stars, dense, compact remnants of once massive stars, also plays a significant role in creating these heavy elements. These star remnants, traveling at incredible speeds and forces, collide in an event so violent that it produces heavy elements in vast quantities, further enriching the universe with the building blocks of life and everything around us. As these elements are spread across the cosmos, they find their way into the interstellar medium, which eventually forms new stars, planets, and even life forms. This cycle of stellar birth, evolution, and death is not only a way of creating heavy elements, but is also fundamental to the chemical evolution of the universe. Supernovae play a crucial role in this process, driving the ongoing expansion and transformation of the cosmos. When massive stars exhaust their nuclear fuel, they can no longer support themselves against their own gravity, leading to a catastrophic collapse that triggers a supernova explosion. This explosion ejects the star's outer layers into the surrounding space, carrying with them the rich elements formed during the star's life. The elements dispersed by these explosions, such as carbon, oxygen, and iron, become part of the medium. This enriched gas and dust spread throughout the galaxy, seeding new generations of stars with the materials they need to form. It is estimated that nearly 75% of the elements that make up the human body were forged in the hearts of stars that eventually exploded as supernovae. Furthermore, these tremendous explosions do more than simply distribute elements. They also influence the dynamics of the galaxy. The shockwaves generated by supernovae compress nearby gas clouds, triggering new star formation. This process acts as a form of cosmic recycling, where the death of one generation of stars contributes to the birth of the next. It's a continuous cycle of creation and destruction, pushing forward the evolution of the universe. Supernovae also help us understand the expansion of the universe itself. Certain types of supernova, specifically type 1a supernova, serve as standard candles for measuring cosmic distances. These occur in binary systems, when a white dwarf star accumulates matter from a companion star, eventually reaching a critical mass and exploding. By measuring the brightness and distance of these explosions, astronomers can gain insights into the rate at which the universe is expanding, offering clues about the role of dark energy in shaping the cosmos. While supernovae play a significant role in the creation and distribution of elements, black holes, those mysterious cosmic objects, have a subtler but equally powerful influence on the universe. Black holes, formed when massive stars collapse under their own gravity at the end of their life cycles, exert extreme gravitational forces. These forces can have a profound impact on the matter around them. When a black hole pulls in matter, it forms an accretion disk, a swirling, spinning mass of material that becomes heated to incredible temperatures. The energy released by the accretion disk can affect the atomic structure of nearby material. Atoms in the vicinity are torn apart, stripped of electrons, and altered in ways that can change their fundamental properties. In this way, black holes play an indirect role in atomic formation. Moreover, black holes can also influence the formation of new stars. Their immense gravity can either trigger or suppress the collapse of gas clouds, which are the building blocks of new stars. This gravitational influence extends beyond the immediate surroundings of a black hole, shaping star formation across vast regions of space. As new stars are born, they eventually reach the end of their life cycles and, through the explosive events of supernova, forge heavier elements. These elements are then spread throughout the cosmos, forming the foundation for new stars, planets, and even life itself. In essence, black holes contribute to the cosmic nucleosynthesis process, indirectly influencing the formation of elements that are essential to life. Their gravitational influence plays a part in the larger cosmic cycle of creation, evolution, and death that shapes our universe. They are but one piece of a vast, intricate cosmic puzzle that continues to unfold across the eons. At the heart of the cosmos, near the supermassive black holes that anchor galaxies, an extraordinary dance of creation and destruction occurs, one that alters the very fabric of atoms. These black holes, known for their intense gravitational pull, create environments where energy reaches extremes that challenge our understanding of the atomic world. While black holes do not directly destroy or create atoms in the traditional sense, their overwhelming influence on the surrounding space leads to extreme cosmic phenomena, such as gamma-ray bursts. These bursts, among the most energetic events in the universe, have the potential to disrupt atomic structures over vast regions, tearing through matter and bending the rules of reality itself. Though the black holes themselves don't actively manipulate atoms on a fundamental level, their gravitational and energetic reach shapes the cosmos in ways that lead to cycles of atomic creation and annihilation. This constant interplay of forces, driven by these giants of space, shapes the very landscape of the universe, sustaining the cosmic tapestry in a perpetual state of flux. Meanwhile, in the subatomic world, quantum mechanics reveals a reality far removed from the classical view of atoms as miniature solar systems. Traditional models once imagined electrons as tiny particles orbiting the nucleus in well-defined, predictable paths, much like planets orbiting the sun. But quantum theory brought with it a radical shift in this understanding. The notion of wave-particle duality tells us that electrons do not follow fixed orbits. Instead, they exist in a state of probability. This probabilistic nature is encapsulated in what is called a wave function, a mathematical construct that describes the likelihood of finding an electron in a particular location at any given time. In this new paradigm, the electron no longer travels along clear-cut paths. Instead, it exists within a cloud of probability, often referred to as an orbital. These orbitals, shaped like spheres, lobes, and more, represent areas where the electron is most likely to be found, rather than guaranteeing its presence at any exact point. The very concept of an orbital suggests that electrons are spread out, their positions uncertain until observed. And when an electron changes energy states, moving between orbitals, it absorbs or emits energy, frequently in the form of light. This is the origin of the distinctive spectra we observe when studying the light emitted by different elements. Another cornerstone of quantum mechanics is the Pauli exclusion principle, which asserts that no two electrons can occupy the same quantum state simultaneously. This principle plays a crucial role in explaining the diverse chemical behaviors of elements. The arrangement of electrons in an atom dictates how atoms bond, interact, and react chemically, which is the very foundation of the material world around us. The way electrons fill orbitals, obeying the Pauli exclusion principle, governs the chemical characteristics of substances, from the simplest to the most complex. As we venture beyond the confines of individual atoms, quantum mechanics continues to shape the world around us. The principles of quantum behavior extend far beyond the microscopic scale, influencing phenomena in the macroscopic world. For example, superconductivity, the ability of certain materials to conduct electricity without resistance, relies entirely on quantum mechanical effects. Similarly, the behavior of semiconductors, foundational to modern electronics, is also governed by quantum laws. In this way, quantum mechanics not only unveils the secrets of the atom, but also forms the bedrock of much of our modern technology, from computers to medical devices. One of the most captivating aspects of quantum theory is wave-particle duality, a concept that reveals how particles like electrons and photons exhibit both wave-like and particle-like properties. This duality challenges the very core of our classical understanding of the physical world, which traditionally classified objects as either waves or particles. At the quantum level, however, the boundaries blur. Under some conditions, particles behave like waves, exhibiting interference patterns when passed through slits or other obstacles. Yet under other conditions, the same particles act as discrete, localized particles. A famous demonstration of wave-particle duality is the double-slit experiment, which shows how particles, when directed through two slits, create an interference pattern typical of waves. However, when scientists attempt to observe which slit an electron passes through, the interference pattern disappears, and the electrons behave like particles. This mind-bending result suggests that the very act of observation changes the behavior of particles at the quantum level, forcing scientists to reconsider the relationship between reality and measurement. In the context of atomic structure, this duality further enriches our understanding of the electron's behavior. Electrons, confined to their orbitals, do not follow rigid, predictable paths. Instead, their movement is defined by the probabilities outlined by the wave function. The clouds of probability, or orbitals, reflect the electron's wave-like nature, indicating regions of space where the electron is likely to be found. Thus, when studying atomic structure, we no longer speak of fixed trajectories, but of fuzzy, probabilistic regions where electrons are most likely to appear. The uncertainty principle, articulated by Werner Heisenberg, challenges even our most basic intuitions about the nature of reality. This principle posits that there is a fundamental limit to how precisely we can know both the position and momentum of a particle at the same time. The more accurately we measure one of these properties, the less accurately we can know the other. This inherent uncertainty forces us to abandon the classical view of particles as having fixed positions and speeds. In practical terms, when it comes to electrons, their locations are not definite and cannot be precisely determined. Instead, we can only speak in terms of probabilities, describing the regions in which an electron is likely to be found. This probabilistic view is foundational to our understanding of atomic orbitals, regions of space where electrons are most likely to be located. Electrons do not trace clear paths around the nucleus. Instead, they exist in these clouds of probability with varying degrees of likelihood attached to each region. This leads to the realization that the precise state of a particle, its position, velocity, or momentum, does not exist independently of our measurement of it. It is only when we observe a particle that its properties seem to collapse into a definite state. The uncertainty principle also forces a paradigm shift in our understanding of reality itself. It suggests that at the quantum level, the act of observation alters the very nature of the observed phenomenon. This notion of an observer-dependent reality is radically different from the deterministic worldview of classical physics. This revolution in thought opened the door to strange and fascinating quantum phenomena, including wave-particle duality and the paradoxes that arise from the microscopic world. In conclusion, quantum mechanics reshapes not only how we view the atom, but also our entire understanding of the universe. From the immense forces surrounding supermassive black holes to the mysterious behavior of electrons, quantum theory continues to redefine the boundaries of science, technology, and philosophy. It tells us that the universe, at its most fundamental level, is not a predictable, deterministic machine, but a fluid, probabilistic system, where observation itself plays a pivotal role in determining reality. The uncertainty principle, one of the cornerstones of quantum mechanics, beckons us to question the very nature of the universe. It invites a deeper exploration into the fundamental building blocks of reality, revealing a world that operates under rules that defy our everyday experiences. In the atomic realm, things do not behave as we expect them to. The uncertainty principle is not just a mathematical abstraction, but a fundamental truth about the nature of existence. By acknowledging the limitations this principle imposes, scientists continue to unravel the complex mysteries of atomic interactions, offering new insights into the very essence of matter itself. One of the most perplexing phenomena that emerge from quantum mechanics is quantum entanglement. This strange and counterintuitive concept suggests that two or more particles can become intricately linked in such a way that the state of one particle can instantaneously affect the state of another, even if the two particles are separated by vast distances that may span light years. This goes against everything we know about space, locality, and the speed of light. The very fabric of reality seems to be more interconnected than we ever imagined. When one particle in an entangled pair is measured, the state of the other particle is instantaneously determined, no matter how far apart the two are. This phenomenon raises profound questions about the nature of reality itself, casting doubt on our traditional understanding of space, time, and communication. The implications of quantum entanglement challenge the very idea of locality, a principle that has governed our understanding of physics for centuries. If the state of one particle is linked to another across vast distances, can information truly be transmitted instantaneously? Could this form of non-locality pave the way for communication systems that transcend the limitations of traditional physics? What we are witnessing here is a breakdown of classical assumptions about cause and effect, as the particles seem to act in perfect synchrony, defying the notion that one particle's state should be a result of the other's. The implications for technology are staggering. The ability to manipulate entangled particles could lead to the development of technologies that are radically different from anything we've ever imagined. In the world of quantum computing, this very phenomenon could be harnessed to revolutionize the way we process information. Imagine computers that operate on entangled qubits, quantum bits that are fundamentally different from classical bits. These qubits could exist in multiple states at once, vastly increasing computational power and speed. With entanglement, quantum computers could perform calculations at unimaginable rates, potentially solving problems that are currently beyond the reach of classical machines. These advances could reshape industries, from cryptography to artificial intelligence, with the power to process vast amounts of data in real time. Entanglement could also offer us new insights into the fundamental forces of nature. If particles are more interconnected than we previously believed, it suggests that the universe operates on a deeper level of connection and interdependence. The study of quantum entanglement could help us probe the interactions between the fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, and ultimately deepen our understanding of the laws that govern the universe. The more we learn about entanglement, the closer we get to solving some of the biggest mysteries of physics, such as the nature of dark matter and dark energy. Advancements in quantum theory have completely transformed our understanding of atomic behavior. In the early 20th century, scientists realized that classical physics, which had successfully explained much of the observable universe, could not account for the peculiar behaviors of subatomic particles. Quantum theory emerged as a revolutionary framework that introduced concepts like wave-particle duality, the idea that particles such as electrons can exhibit properties of both waves and particles. This insight led to the development of models that accurately describe the structure of the atom, allowing scientists to predict how atoms behave under different conditions. The advent of quantum mechanics replaced older classical models that couldn't explain the complexity observed in atomic interactions. For example, the introduction of quantum states allowed scientists to predict electron arrangements around the nucleus, explaining the periodic table's structure and the chemical properties of elements. These quantum mechanical models, which describe the behavior of electrons and other subatomic particles, have provided a much more accurate and nuanced understanding of atomic structure. In addition to transforming our understanding of atomic interactions, quantum mechanics has driven the development of groundbreaking technologies that have reshaped the modern world. Innovations such as quantum computing and quantum cryptography rely heavily on the principles of quantum mechanics to perform tasks that classical technologies simply cannot. Quantum cryptography, for instance, utilizes the peculiar properties of quantum states to create secure communication systems that are impervious to eavesdropping. These technologies promise to revolutionize not only computing power, but also the security of information, offering new methods for protecting sensitive data in an increasingly interconnected world. Furthermore, recent advancements in atomic research have uncovered even more mind-bending phenomena like quantum entanglement and superposition. These discoveries push the boundaries of our understanding and inspire new lines of inquiry that extend beyond physics into fields such as materials science, cosmology, and biology. The profound interconnectedness of all scientific knowledge is becoming ever more apparent as researchers begin to see the connections between seemingly disparate areas of study. The more we understand about quantum mechanics, the more we realize that the universe is a deeply interconnected and complex system. At the heart of all matter, there are four fundamental forces that govern the interactions between particles. These forces are responsible for the structure and behavior of everything in the universe, from the smallest atoms to the largest galaxies. Gravity, the weakest of these forces, plays a critical role in shaping the large-scale structure of the universe. It governs the orbits of planets and stars and pulls matter together to form galaxies and black holes. However, on the atomic scale, gravity's influence is negligible, dwarfed by the stronger forces that govern the behavior of subatomic particles. The second fundamental force, electromagnetic force, is far stronger than gravity and is responsible for the interactions between charged particles such as protons and electrons. This force is crucial for holding electrons in their orbits around atomic nuclei, and it gives rise to essential phenomena like electricity, magnetism, and light. Without it, chemical bonds and the vast range of material interactions we encounter in our daily lives would not exist. The third fundamental force, the weak nuclear force, plays a key role in processes like radioactive decay and nuclear fusion. While the weak force doesn't directly bind atoms together, it enables certain types of nuclear reactions to take place. This force is vital for the life cycles of stars, helping to fuel the process of stellar nucleosynthesis, the formation of elements in the hearts of stars, and for the creation of the elements that make up the world around us. Finally, the strong nuclear force, the most powerful of the four, holds atomic nuclei together. It binds protons and neutrons in the nucleus of an atom, overcoming the electromagnetic repulsion between positively charged protons and ensuring the stability of matter at the most fundamental level. Without the strong force, atomic nuclei would disintegrate and matter as we know it would not exist. In summary, quantum mechanics and atomic theory have radically reshaped our understanding of the universe. From the mysterious behaviors of particles at the atomic scale to the profound interconnections that bind everything together, we are entering a new era of scientific discovery. As we continue to delve deeper into the fundamental forces and principles that govern the cosmos, we are likely to uncover even more astonishing insights, each one pushing the boundaries of what we thought was possible. This journey into the atomic and quantum realms not only transforms our understanding of the universe, but also opens the door to technological innovations that will redefine the future. The universe is governed by four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces, each with distinct characteristics and roles, shape the very fabric of reality, determining everything from the structure of atoms to the behaviors of distant stars. Among these, the strong nuclear force is both the most powerful and the most enigmatic. Operating only at the tiniest of distances, on the scale of about 1 femtometer or 1/1,000,000th of a billionth of a meter, this force holds protons and neutrons together within atomic nuclei. Without it, atomic nuclei would break apart, and the elements that make up the matter around us would cease to exist in the form we recognize. Protons, which all carry a positive charge, naturally repel one another due to electromagnetic forces. But the strong nuclear force, which overcomes this electromagnetic repulsion, binds these protons together with such intensity that it keeps atomic nuclei stable. This intricate interplay between forces is responsible for the very existence of elements, from the simplest hydrogen atom to the heaviest known isotopes. While the strong nuclear force is immensely powerful, it only operates within a very narrow range. It's the force that ensures the stability of atomic nuclei, but it is also the force that limits the size of atoms. For larger atoms, the presence of neutrons, particles with no charge, is essential. Neutrons serve to stabilize atomic nuclei, helping to balance the repulsive forces between protons and allowing larger elements to exist. If the number of neutrons in an atom's nucleus deviates too far from its protons, the nucleus becomes unstable and undergoes radioactive decay. This phenomenon is crucial to the ongoing processes of stellar evolution and the formation of new elements in stars. Equally vital is the electromagnetic force, which governs the interactions between atoms and molecules. Unlike the strong nuclear force, which binds particles within the nucleus, the electromagnetic force operates across a much larger range, influencing how atoms bond to form molecules. It arises from the interaction between positively charged protons in an atom's nucleus and the negatively charged electrons that orbit it. When two atoms approach one another, their electrons and nuclei experience electromagnetic attraction, which can lead to the formation of chemical bonds. There are two primary types of chemical bonds that arise from this electromagnetic interaction: ionic bonds and covalent bonds. In an ionic bond, one atom donates an electron to another, resulting in the creation of oppositely charged ions. The attractive force between these ions holds them together, as seen in common table salt, where sodium donates an electron to chlorine. This transfer creates a strong ionic bond due to the difference in their charges. In contrast, covalent bonds form when two atoms share electrons. This sharing allows both atoms to achieve a more stable electron configuration, lowering their overall energy. The electromagnetic attraction between the shared electrons and the positively charged nuclei creates a balance that keeps the atoms together. A well-known example of covalent bonding is the water molecule, in which each hydrogen atom shares an electron with the oxygen atom, resulting in a stable molecule. These interactions also give rise to weaker forces like hydrogen bonding, which, though not as strong as covalent bonds, plays a crucial role in determining the properties of substances like water and in the structure of complex biological molecules, including DNA. The ability of water molecules to hydrogen bond gives water its unique properties, such as its high boiling point and surface tension, and allows it to support life in a way few other substances can. As we delve deeper into the weak nuclear force, we enter the realm of particle decay. While the strong nuclear force is responsible for holding protons and neutrons together, the weak nuclear force is involved in changing one type of particle into another. This process is crucial for the stability of certain isotopes and plays a key role in the generation of elements. One of the most prominent manifestations of the weak nuclear force is beta decay, a type of radioactive decay where a neutron in an unstable atomic nucleus is transformed into a proton, emitting a beta particle, a high-energy electron, and a neutrino. The weak force operates on a scale even smaller than that of the strong force, and it is essential for the transformation of quarks, the fundamental building blocks of protons and neutrons. In beta decay, a down quark within a neutron changes into an up quark, resulting in the neutron turning into a proton. This process alters the atomic number of the element, thus creating a new element. The emitted neutrino, a nearly massless particle, carries away some of the energy from the decay. The weak nuclear force is not only important in atomic decay, but also in stellar processes, such as the fusion reactions that power stars and the interactions of neutrinos, which are incredibly elusive due to their ability to pass through matter without interacting. These four forces, strong nuclear, weak nuclear, electromagnetic, and gravity, are the invisible threads that weave the universe together, governing everything from the behavior of subatomic particles to the vast structures of galaxies. Without them, the universe would be a very different place, and life as we know it would not exist. Understanding these forces, how they interact, and how they shape the matter around us allows us to appreciate the profound complexity of the cosmos and our place within it. In the vast and intricate cosmos, atomic forces, particularly the weak nuclear force, play an essential yet often overlooked role in shaping the universe as we know it. These forces govern phenomena that are critical to the evolution of stars, the creation of elements, and the very fabric of the universe. Without the weak nuclear force, the delicate processes that sustain life and the elements we are made of simply wouldn't exist. One of the most profound effects of the weak nuclear force is its influence on isotopes and their decay processes. Isotopes, atoms of the same element with different numbers of neutrons, undergo weak interactions which trigger the release of energy and result in the transformation of one element into another. In stars, these processes happen continuously, generating the energy we perceive as starlight and providing the heat necessary for life to thrive on planets. Without the weak force, these processes would not occur in the same way, and elements like carbon, oxygen, and nitrogen, fundamental to life, would never have been created or would remain unstable, preventing the formation of the complex chemistry that makes our world possible. On a much larger scale, weak interactions have far-reaching consequences that extend well beyond the decay of individual isotopes. They are fundamental to our understanding of particle physics and the broader evolution of the universe. Without the weak force, the cosmos as we understand it would look radically different, and the universe's chemical diversity would be significantly diminished. The intricate interplay of forces that governs the formation and decay of atoms thus acts as the bedrock of everything from the stars themselves to the molecules that constitute life. This brings us to the fascinating and enigmatic concept of antimatter. While matter, the substance that makes up all that we can see and touch, is composed of particles like electrons, protons, and neutrons, antimatter is made of the corresponding antiparticles. Each particle of matter has a counterpart in antimatter. For example, the electron with its negative charge has a counterpart called the positron, which has the same mass but carries a positive charge. This fundamental difference in charge is crucial when examining the relationship between matter and antimatter. When matter and antimatter come into contact, they annihilate each other in a dramatic release of energy. The annihilation occurs because the matter and antimatter particles embody opposite properties, opposite charges, spins, and other characteristics, which leads to their volatile and energetic interactions. Instead of simply interacting like normal atoms, where particles form bonds or push each other away, when matter and antimatter meet, they convert their mass entirely into energy. This phenomenon, described by Albert Einstein's famous equation E equals mc squared, releases an extraordinary amount of energy. Even a tiny quantity of matter and antimatter, when brought together, can produce a vast energy output. The concept of antimatter is not just a curiosity of particle physics. Its implications extend far beyond theoretical science, raising profound questions about the very nature of the universe. One of the most puzzling questions scientists are grappling with is why, despite the symmetrical laws of physics, the universe seems to contain far more matter than antimatter. While scientists can create small amounts of antimatter in laboratories, its natural occurrence in the universe is almost non-existent. This apparent imbalance between matter and antimatter remains one of the deepest mysteries in modern physics and cosmology. The exploration of antimatter and its interactions with matter has significant practical implications as well. Antimatter is already playing a role in advanced technologies, such as positron emission tomography, PET scans used in medical imaging. These interactions could also hold the key to future energy sources, where controlled antimatter annihilation could one day produce vast amounts of energy. The study of antimatter is not only a quest for understanding the fundamental laws of the universe, but also a pursuit that may lead to revolutionary technologies. The birth and evolution of the universe itself began in an incredibly hot and dense state known as the Big Bang, around 13.8 billion years ago. In the aftermath of this event, the universe began to cool, and simple atoms, primarily hydrogen and helium, formed. These primordial atoms served as the building blocks for all the matter that would come to populate the universe. Over time, regions of higher density began to attract more matter due to gravity, forming vast clouds of gas known as nebulae. Within these nebulae, atoms began to cluster together, leading to the formation of the first stars. It was within these stars that the process of nuclear fusion began. Through fusion, hydrogen atoms fused together to form helium, and later heavier elements such as carbon, oxygen, and iron. These elements were essential for the formation of planets, moons, and other celestial bodies. The nuclear fusion process not only generated energy to power the stars, but also created the diverse array of elements required for life as we know it. The evolution of stars is far from a simple process. As stars age, they undergo dramatic transformations, and many eventually reach the end of their life cycles in spectacular cataclysmic events known as supernovae. These explosions are not just destructive, they scatter newly created elements and atoms across space, enriching the interstellar medium and providing the raw materials for the formation of new stars and planets. This constant cycle of birth, death, and rebirth in the stellar population is a driving force behind the ongoing evolution of galaxies. As stars continue to form and die, they contribute to the dynamic structure of galaxies. Galaxies themselves are vast collections of stars, gas, dust, and dark matter, often containing billions of stars and countless planetary systems. These galactic structures have been shaped over billions of years by the interactions of countless atoms and the forces that govern their behavior. The interplay of gravity, electromagnetic forces, and nuclear forces has created an intricate cosmic tapestry, where the formation of stars and planets is intertwined with the death and rebirth of other stars. The complexity of the universe's atomic landscape extends down to the very composition of planets like Earth. Earth, like all other planets, is made up of a rich array of atoms and elements, many of which were formed in stars long before our solar system took shape. The presence of liquid water, carbon-based life, and the diverse range of minerals found on Earth are the result of billions of years of atomic interactions influenced by factors like time, temperature, and pressure. In essence, the universe is a grand symphony of atomic interactions. From the formation of galaxies to the birth of life on Earth, atoms are the fundamental building blocks that govern everything. The weak nuclear force antimatter and the processes of stellar evolution all play vital roles in the complex and ever-evolving cosmos. As we continue to explore these atomic processes, we uncover more about the delicate balance of forces that shape the universe and our place within it. The study of atoms goes far beyond the simple understanding of what they are composed of. It reaches into the very fabric of the universe, exploring the profound impact they have on the cosmos. Atoms not only form the building blocks of matter, but also emit and absorb electromagnetic radiation. This radiation is crucial for our ability to observe distant stars and galaxies, providing invaluable insight into their properties and the evolution of the universe over billions of years. Therefore, atoms are not just the fundamental units that make up all things. They are the architects of the universe itself, shaping everything we see and experience. Dark matter and dark energy stand as two of the most mysterious and elusive elements in our quest to understand the cosmos. Together, they make up a significant portion of the universe's mass and energy. Dark matter, which accounts for about 27% of the universe, is particularly enigmatic because it neither emits, absorbs, nor reflects light. Its presence is inferred not by direct observation, but by its gravitational effects on visible matter. This unseen force is crucial in holding galaxies together, preventing them from flying apart due to the sheer speed at which they rotate. Without dark matter, the stars within galaxies would not have enough gravitational binding to stay in place. Despite its invisibility, dark matter's gravitational influence is evident in many cosmic phenomena. One of the most striking examples of this is the way galaxies rotate. The outer regions of galaxies spin at speeds that, without the unseen mass of dark matter, would be too fast for the galaxies to maintain their structural integrity. Furthermore, dark matter's presence is detectable through gravitational lensing, a phenomenon in which light from distant objects bends around massive clusters of matter. This effect provides a glimpse into the hidden universe, revealing the invisible framework upon which visible matter is built. On the other hand, dark energy comprises roughly 73% of the universe and plays a completely different role. It is thought to be the driving force behind the accelerated expansion of the universe. Unlike dark matter, which has an attractive gravitational pull, dark energy seems to exert a repulsive force on the vast scales of space. This mysterious form of energy was first identified in the late 20th century when observations of distant supernovae revealed that the expansion of the universe was speeding up rather than slowing down, as had been previously assumed. Despite its prominence, dark energy remains poorly understood. It is hypothesized to be intrinsic to space itself, potentially linked to the concept of vacuum energy in quantum physics. Although it does not interact with normal matter in the same direct manner as dark matter, dark energy profoundly influences the universe's large-scale structure. It drives the expansion of space, pushing galaxies and clusters of galaxies further apart. This expansion will ultimately affect the fate of the universe, influencing the future of all celestial bodies, and potentially even determining whether the universe will continue to expand indefinitely or eventually collapse in on itself. Together, dark matter, dark energy, and normal matter form the three pillars that govern the universe's structure and evolution. While scientists have made tremendous progress in understanding the interactions between these forces, much about them remains a mystery. The interplay of these components determines the large-scale behavior of the universe, including the formation of galaxies, the clustering of matter, and the eventual outcome of cosmic evolution. As we turn our attention to the potential for life beyond Earth, the role of atoms becomes even more critical. The abundance and distribution of specific atoms are key factors in determining the likelihood of life elsewhere in the universe. Atoms, as the fundamental units of matter, combine in various ways to form molecules. These molecules, in turn, are the building blocks of life as we know it. Among the most essential elements for life are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, often referred to as the life elements. Their presence in different environments significantly impacts the probability that life could arise and thrive there. When astronomers search for signs of life on other celestial bodies, they focus on regions that are rich in these essential elements. Carbon, for example, is the backbone of organic molecules and the fundamental building block of life. The detection of organic compounds on other planets or moons raises the tantalizing possibility that life might exist or might have once existed there. Water, another critical component of life, is also made up of atoms, 2 hydrogen atoms bonded to 1 oxygen atom. The discovery of liquid water, or even water ice, on other planets or moons sparks hope for the existence of life forms in those environments. The distribution of these essential atoms is not just about their mere presence, but also their placement in the cosmos. Planets and moons that lie within the habitable zone of a star, where temperatures are conducive to sustaining liquid water, are particularly promising in the search for life. In addition to the location, geological activity is another important factor. Regions with active geology can transport nutrients, create diverse environments, and foster the atomic interactions necessary for biological processes. These factors make certain celestial bodies more promising for the development of life, even if they do not seem hospitable at first glance. Subsurface features, such as liquid water trapped beneath the surface of a moon, may hold untapped potential for life. In essence, the universe is a vast and interconnected web of atoms, forces, and energy, with each component playing an indispensable role in shaping the cosmos. Whether in the form of invisible dark matter holding galaxies together, or the atoms that create the building blocks of life, these elements reveal the intricate and dynamic nature of our universe. The continued study of these phenomena promises to uncover more of the secrets that lie at the heart of everything we know and everything we have yet to discover. Our understanding of life's incredible adaptability offers profound insights into the resilience of biological systems, showcasing life's ability to thrive in conditions that, at first glance, seem hostile and uninhabitable. On Earth, life flourishes in extreme environments, from the depths of the ocean to areas bathed in intense radiation. These findings demonstrate that life is not confined to narrow conditions and can endure in a wide range of environmental and atomic settings. This adaptability sparks an intriguing question. Might life elsewhere in the universe rely on entirely different chemical processes or even alternative elements? This broadens our perspective on what life can be, suggesting that the very essence of life could be more diverse than we have ever imagined. As humanity continues to push the boundaries of space exploration, the quest to identify the right atomic mixtures for sustaining life remains a cornerstone of astrobiology. Atoms, the fundamental units of matter, play a pivotal role in the formation of the complex chemical reactions that give rise to the diversity of planetary systems. Composed of protons, neutrons, and electrons, atoms combine in countless ways to form molecules. The distinctiveness of these molecules arises from how atoms bond, and it is this very variety that sparks the astounding diversity of life and matter across the universe. With more than 100 elements cataloged in the periodic table, each element possesses unique properties, allowing it to interact in specific ways with other elements. This ability to form diverse chemical compounds is at the heart of life's complexity. Carbon, in particular, plays an essential role in creating organic compounds, which are the fundamental building blocks of life. When carbon bonds with other elements such as hydrogen, oxygen, and nitrogen, it forms molecules crucial for life processes. These molecules include amino acids and nucleotides, which serve as the foundation for proteins and genetic material, both of which are essential for the functioning of biological systems. Moreover, the synthesis of complex molecules is not a process confined to Earth alone. Stars, the engines of the universe, drive the chemical reactions that forge new elements and molecules, leading to the rich diversity of chemistry that unfolds across planets and solar systems. These reactions, fueled by the immense energy produced by stars, create the conditions for life's building blocks to emerge, potentially even in far-flung regions of space. The environment surrounding atoms and molecules plays an equally important role in shaping chemical diversity. Planets, each with their unique environmental conditions, ranging from temperature and pressure to the presence or absence of water, directly influence the chemical processes that take place. A planet located in a cold, distant part of its solar system may see the formation of icy compounds, while those closer to the heat of a star could generate more gaseous substances. This variability contributes to the unique chemical fingerprints of each planetary system, creating a rich tapestry of potential environments for life to evolve. The dynamic interplay between the elements, combined with the diverse conditions found throughout the cosmos, leads to an extraordinary variety of chemical compounds. This vast spectrum of chemistry forms the backbone of planetary systems, whether it's the rocky terrain of Earth or the swirling gas clouds of Jupiter. It is within these chemical frameworks, shaped by the elements and the environment, that the universe's vast diversity of worlds and life forms comes into being. Modern science has developed a range of sophisticated tools and technologies to delve into the atomic level and explore the fundamental behaviors of atoms. One such method is atomic force microscopy, AFM, which has revolutionized our ability to visualize individual atoms. This technique scans a sharp tip across the surface of a sample, producing extraordinarily high-resolution images that reveal the intricate arrangement of atoms within various materials. AFM is invaluable in fields such as nanotechnology and material science, where understanding atomic structure is critical to innovation. Another groundbreaking technique is scanning tunneling microscopy, STM, which uses a sharp tip to scan the surface of a material without direct contact. Instead, STM employs the principle of quantum tunneling to detect the tiny currents that occur as the tip moves just above the surface. This allows scientists to capture atomic-level images and even manipulate individual atoms, pushing the boundaries of what is achievable at the nanoscale. Furthermore, particle accelerators such as the Large Hadron Collider, LHC, take atomic exploration to unprecedented levels. These colossal machines accelerate particles to nearly the speed of light and smash them together in high-energy collisions. These experiments enable physicists to probe the deepest mysteries of matter, uncovering fundamental particles like quarks and leptons. Insights gained from such experiments have transformed our understanding of the universe, particularly with regard to the Higgs boson, a particle integral to our comprehension of how particles acquire mass. Through these groundbreaking tools, we are not only learning more about the fundamental building blocks of life and matter, but also unlocking the secrets of the cosmos itself. Thus, our exploration of the atomic realm, coupled with the discovery of new chemical processes and environments, continues to expand our understanding of life's potential in the universe. Whether through deep space missions or advances in laboratory technologies, we are gaining new insights into the vast diversity of conditions that could sustain life. And in doing so, we are rethinking the very nature of life itself. In recent years, groundbreaking techniques like laser spectroscopy have empowered scientists to delve deep into the intricate world of atomic and molecular energy levels. By using high-intensity lasers, this method excites atoms and molecules, providing invaluable insights into their structural and behavioral characteristics. As atoms are subjected to intense laser light, they emit or absorb energy, revealing detailed data on their unique energy states. These insights not only advance our understanding of atomic interactions, but also lay the groundwork for technologies that enhance our comprehension of the atomic universe. Alongside laser spectroscopy, advancements in particle physics have radically transformed our knowledge of the fundamental building blocks of matter. Researchers investigating subatomic particles have revealed a complex and sophisticated framework for how these tiny particles interact. Discoveries of particles such as quarks and leptons have shattered the long-held belief that atoms were indivisible, showing that they are, in fact, made up of even more minuscule components. This revelation has forced scientists to reconsider the traditional model of atomic structure, paving the way for more refined theories. To further explore these hidden realms of matter, high-energy particle accelerators have become indispensable. These sophisticated devices accelerate particles to near light speed and collide them under controlled conditions, mimicking the extreme environments that existed right after the Big Bang. For example, in facilities like the Large Hadron Collider, LHC, scientists explore the fundamental forces that govern particle behavior. The discovery of the Higgs boson in 2012, for instance, illuminated our understanding of how particles acquire mass, an essential building block of the universe's structure. These particle collisions reveal not only the nature of atomic forces, but also challenge and refine current scientific theories, particularly the Standard Model of particle physics. Beyond theoretical implications, particle physics has far-reaching practical applications. The technologies developed to detect and image particles have found vital roles in other fields, such as medicine. Cutting-edge imaging techniques are now used in cancer treatments and diagnostic imaging, offering life-saving solutions. Thus, the exploration of atomic particles has an undeniable impact on both our scientific knowledge and technological progress, significantly improving human life in areas beyond fundamental science. In parallel, the field of atomic visualization has also made extraordinary strides. The advent of techniques like scanning tunneling microscopy, STM, has revolutionized how we observe matter at the atomic scale. By utilizing quantum tunneling, STM allows researchers to observe individual atoms on a surface with an unparalleled level of resolution. This breakthrough has enabled scientists to visualize and understand the structure of materials at a scale once considered unattainable. STM has been instrumental in examining materials at the atomic level, unveiling previously hidden details about their structure and properties. Another key development in atomic visualization is transmission electron microscopy, TM. TM uses a beam of electrons transmitted through a thin specimen, allowing scientists to capture high-resolution images of atomic structures and examine the electronic properties of materials. This technique has proven essential in studying materials like semiconductors and metals, offering vital insights that contribute to advancements in technology and material science. The field has also benefited from innovations in X-ray imaging. The introduction of X-ray free electron lasers has provided a new level of precision, enabling scientists to observe atomic processes in real time. These high-energy X-ray pulses are fast enough to capture the movement of atoms during chemical reactions, offering an unprecedented window into dynamic systems. This breakthrough is set to fuel advancements in material science, chemistry, and even biology, allowing for deeper explorations of the atomic landscape. These imaging techniques not only push the boundaries of scientific discovery, but also lay the foundation for the creation of new, more efficient materials. By studying the atomic structure of substances, researchers can design better energy storage systems, develop innovative electronic devices, and explore new materials that could have transformative effects on industries ranging from energy to technology. The study of atomic interactions extends beyond the realm of pure science into practical applications such as nuclear fusion and fission, which are essential for sustainable energy production. Nuclear fusion, the process that powers the sun, occurs when light atomic nuclei merge to form a heavier nucleus, releasing vast amounts of energy. Understanding how to replicate this process on Earth has become a central focus of research aimed at providing a clean, virtually limitless source of energy. The study of atomic particles like protons and neutrons is essential to unlocking the mechanisms of fusion, enabling researchers to simulate the extreme conditions found in the core of stars, where temperatures and pressures are high enough to facilitate fusion reactions. Conversely, nuclear fission, the process that powers current nuclear reactors, involves the splitting of heavy atomic nuclei into smaller fragments, releasing energy. The study of isotopes like uranium-235 and plutonium-239 has been key to understanding how fission can be harnessed for energy production. Research in this area has led to significant improvements in nuclear reactor safety protocols and reactor design, making fission a more efficient and safer energy source. Both fusion and fission research benefit from advances in particle physics, material science, and plasma physics. Instruments like particle accelerators and spectrometers play crucial roles in exploring atomic interactions and laying the groundwork for breakthroughs in energy generation. Ultimately, the ongoing exploration of atomic structure, particles, and forces continues to shape the future of science and technology. With each discovery, we gain new insights into the universe's fundamental building blocks, while also developing technologies that enhance our daily lives. The journey to unravel the mysteries of the atomic world not only deepens our understanding of the cosmos, but also paves the way for practical applications that could revolutionize energy production, medical diagnostics, and countless other industries. The intricate and foundational forces that govern atomic interactions play an essential role in shaping the future of energy production and consumption. Delving deep into how atoms bond, split, and interact allows us to move closer to harnessing these processes in ways that could revolutionize the global energy landscape. As scientists continue their relentless exploration of atomic physics, breakthroughs are pushing the boundaries of human knowledge, particularly in the pursuit of cleaner, more efficient energy solutions. At the core of this effort lies nuclear fusion, a process where two light atomic nuclei, typically isotopes of hydrogen, fuse to form a heavier nucleus. This reaction, which takes place under the extreme temperatures and pressures found at the heart of stars, releases vast amounts of energy. The mechanics behind fusion, driven by the strong nuclear force, hold the potential to provide humanity with an abundant and environmentally clean energy source. Unlike traditional fossil fuels, fusion could offer a sustainable and nearly limitless source of power without the devastating environmental consequences associated with current energy production methods. However, despite its promise, achieving controlled nuclear fusion on Earth remains an immense challenge. The conditions required to replicate the natural processes of stars, extreme heat and pressure, have proven difficult to recreate in a laboratory setting. Yet, as technology advances, researchers are edging closer to realizing this dream, and each step forward brings us closer to a new era of energy production. In contrast, nuclear fission, the process by which a heavy atomic nucleus such as uranium or plutonium splits into smaller nuclei, has already been harnessed to generate energy. This method, widely used in nuclear power plants, also releases vast amounts of energy, but it comes with significant challenges, including safety concerns and the disposal of radioactive waste. Nevertheless, nuclear fission remains a cornerstone of our energy infrastructure, providing a substantial portion of the world's electricity. The energy produced by both fusion and fission arises from the conversion of mass into energy, as explained by Einstein's famous equation. This concept highlights the tremendous potential of atomic energy, whether in the sun's fusion reactions or in the fission reactors that power cities across the globe. Moreover, atomic physics is not just about understanding these complex reactions. It's about exploring and manipulating the underlying quantum properties that govern the behavior of matter at the smallest scales. The rise of quantum technologies, such as quantum computers and sensors, has opened up new possibilities for manipulating atoms in ways that were previously unimaginable. Quantum mechanics, with principles like superposition and entanglement, enables us to observe and control atomic behaviors that challenge classical physics. These quantum effects, once thought to be limited to the microscopic world, could soon be harnessed to unlock unprecedented insights into atomic structures and interactions. One promising area of research in quantum technologies is the development of quantum computers, which promise to revolutionize fields ranging from cryptography to materials science. By leveraging the unique properties of quantum bits, qubits, these computers could solve problems far beyond the capabilities of classical machines. The potential applications in atomic physics are profound, as quantum computers could simulate atomic interactions with incredible precision, leading to breakthroughs in everything from nuclear fusion to the development of novel materials for energy storage. In parallel with quantum technologies, scientists are investigating the behavior of atoms at extremely low temperatures, near absolute zero. At these temperatures, atoms begin to exhibit unusual quantum phenomena on a macroscopic scale, creating opportunities for new experiments and insights. By cooling atoms to near freezing conditions, researchers can observe quantum effects like Bose-Einstein condensates and fermionic superfluids, which challenge traditional notions of matter. These experiments not only shed light on the fundamental laws of physics, but also offer clues to the conditions that existed in the early universe, helping us understand how the universe and the forces governing it came into being. In addition, advancements in imaging techniques, such as atomic force microscopy and advanced electron microscopy, allow scientists to study atomic structures with unprecedented precision. These tools enable the direct observation of atomic responses to various stimuli, such as electromagnetic fields or changes in temperature. Such observations are critical for refining existing theories of atomic behavior and discovering new properties that could lead to the development of novel technologies. As our ability to visualize atoms improves, so too does our understanding of the forces that shape the microscopic world. Another fascinating direction of research focuses on the interactions between atoms and external fields, particularly electromagnetic and gravitational waves. Understanding how atoms respond to these forces could be the key to unifying the fundamental forces of nature, one of the most profound goals of theoretical physics. If researchers succeed in understanding how atoms behave under the influence of these fields, it could lead to groundbreaking discoveries that reshape our understanding of space, time, and the very fabric of reality. These fields of atomic research are not just about scientific curiosity, they have practical implications for energy production, especially in renewable energy technologies. The atomic structure of materials plays a pivotal role in determining how efficiently energy is captured, converted, and stored. Take solar energy, for example. Photovoltaic cells, which power solar panels, rely on the behavior of atoms in semiconductor materials like silicon. When sunlight strikes these materials, it excites electrons, creating an electric current. The efficiency of solar panels depends on the atomic properties of the materials used, including their ability to absorb light and conduct electricity. Similarly, in wind energy technologies, the materials used to construct wind turbines must be carefully chosen for their atomic properties. The strength, weight, and resistance to environmental factors like corrosion are all influenced by the atomic structure of the materials. The longevity and performance of wind turbines in fluctuating weather conditions depend heavily on the atomic composition of the materials, particularly their ability to resist fatigue over time. In the realm of bioenergy, the atomic composition of organic matter is crucial for optimizing the conversion of biomass into fuel. By breaking and reforming chemical bonds between atoms, biomass can be transformed into energy-rich compounds. Understanding the molecular structure of different types of biomass allows researchers to fine-tune the conversion processes, making them more efficient and sustainable. This research could be instrumental in developing cleaner, more efficient ways to produce energy from renewable sources. The study of atomic physics, then, is not merely about understanding the minutiae of atomic interactions, but about leveraging that knowledge to create practical solutions to global challenges. Whether through the development of nuclear fusion, advancements in quantum computing, or innovations in renewable energy technologies, the future of energy is deeply intertwined with our understanding of atoms and their behaviors. As researchers continue to push the boundaries of what we know, the potential for new discoveries and breakthroughs grows, offering hope for a cleaner, more sustainable energy future. Advancements in energy storage have long been at the forefront of technological innovation. At their core, technologies such as batteries rely heavily on atomic interactions to function. One of the most significant examples of this is lithium-ion batteries, which depend on the movement of lithium ions between electrodes to store and release energy. These atomic movements allow for the efficient cycling of energy within the battery, a crucial process that powers everything from smartphones to electric vehicles. The ongoing research into atomic behavior in various materials is a driving force behind the evolution of more efficient and sustainable renewable energy solutions. This research highlights how deeply atoms are woven into the fabric of this technological revolution. At the atomic level, energy conversion plays a critical role in understanding the chemical reactions that underpin modern energy systems. At its essence, chemistry is the study of atomic and molecular interactions, transformations, and energy changes. When a chemical reaction occurs, bonds between atoms are either broken or formed, and this process is intricately tied to energy exchanges. Reactions that release energy are known as exothermic reactions, where the breaking and forming of bonds produce energy, often in the form of heat. In contrast, endothermic reactions absorb energy, causing their surroundings to cool as they proceed. This flow of energy is what dictates the direction of chemical reactions, explaining why some reactions occur spontaneously while others do not. A key concept in understanding energy in chemical reactions is potential energy. Atoms have a certain amount of energy inherently stored within their bonds, referred to as potential energy. When these bonds are rearranged during a reaction, the potential energy either increases or decreases. This shift can lead to the release of kinetic energy or, conversely, the absorption of energy. Understanding this dynamic is fundamental in grasping how energy flows through systems, whether in chemical reactions or energy storage devices like batteries. Another critical element in chemical reactions is activation energy. This is the minimum energy required to initiate a reaction by allowing reactants to collide effectively. The activation energy acts as a barrier that determines the rate at which a reaction occurs. Catalysts, which lower the required activation energy, play an essential role in speeding up chemical reactions and are key in fields ranging from energy storage to pharmaceuticals. Furthermore, electron configurations are vital to understanding how atoms interact at the most fundamental level. Electrons occupy specific energy levels within atoms, and when atoms interact, their electrons shift between these levels. This transfer of energy through electron movement is what ultimately drives the formation of products from reactants in a chemical reaction. By manipulating electron behavior, chemists can control and predict the outcome of reactions, which has profound implications for material science, energy storage, and even drug development. The ability to manipulate atoms opens up exciting possibilities for energy storage and transfer. Scientists are exploring how to design materials with tailored properties that enhance energy storage efficiency. For instance, by arranging atoms in specific configurations, researchers can create batteries that are lighter, last longer, and charge more quickly than existing technologies. One such development is the rise of lithium-sulfur batteries, which offer the potential for much higher energy densities compared to traditional lithium-ion batteries. These breakthroughs could significantly increase the capacity of energy storage systems, powering everything from electric vehicles to more efficient renewable energy infrastructures. Additionally, advancements at the atomic level could lead to more effective energy transfer mechanisms. By designing materials with improved conductivity, researchers aim to create systems that minimize energy loss during transmission. This is especially crucial in the context of smart grids, where efficiency is key to maintaining the stability and reliability of energy distribution from diverse sources such as solar and wind power. Efficient energy transfer not only maximizes the utility of renewable energy sources, but also ensures their integration into existing power systems. Beyond storage and transfer, atomic-scale innovations also hold the promise of breakthroughs in energy harvesting. Researchers are investigating materials that can capture waste heat or light with unparalleled efficiency, opening the door to entirely new ways of generating energy. These advancements could lead to technologies that harness previously untapped sources of power, making energy systems even more sustainable. As we continue to delve deeper into the manipulation of atoms, we are poised to redefine what is possible in the realm of energy. The future of energy may be cleaner, more sustainable, and more efficient, thanks to the atomic-level innovations currently being explored. From enhancing energy storage and improving transfer systems to capturing energy from unconventional sources, the possibilities are boundless. One area where atomic energy has already had a profound impact is in the context of nuclear power. Nuclear reactions, which release vast amounts of energy with minimal greenhouse gas emissions, provide an alternative to fossil fuels in electricity generation. Unlike coal or natural gas plants, nuclear facilities do not emit carbon dioxide during operation, making them an attractive option for reducing overall emissions. As the world grapples with the challenges of climate change, nuclear power has become an increasingly important part of the global energy mix. The shift towards cleaner, more sustainable energy sources like nuclear power offers a promising path to mitigating air pollution and combating global warming. Nuclear energy, when harnessed responsibly, could play a critical role in addressing the environmental challenges of our time, providing a reliable and low-emission source of electricity while reducing the harmful effects of burning fossil fuels. The integration of atomic science into energy systems, whether through advanced batteries, more efficient energy transfer, or nuclear power, offers a glimpse into a future where energy is both abundant and sustainable. The continued study of atomic interactions and energy conversion holds the key to unlocking new, more efficient methods of energy storage, transfer, and production, making it an essential component of our efforts to build a cleaner, more sustainable world for future generations. The link between atomic energy and its potential to fuel the future is undeniable, yet it also stirs up serious concerns about the safety of radioactive waste and the looming specter of catastrophic accidents. As governments, scientists, and policymakers explore the promise of nuclear energy, it is crucial to navigate these issues with the utmost care. The challenge lies not only in harnessing atomic energy to meet today's energy demands, but also in understanding its long-term implications for our planet's health. This dynamic conversation weaves together the need for sustainable energy policies with the realities of managing the complexities of nuclear energy. Atomic energy, often heralded as a promising source of power, holds the potential to revolutionize our energy systems. However, its benefits come with a responsibility to ensure that its entire life cycle, ranging from the extraction of uranium to the decommissioning of reactors, is managed with meticulous attention. The question of radioactive waste disposal, for example, is a critical issue that cannot be overlooked. The dangerous byproducts of nuclear energy present a significant challenge in terms of safety, long-term environmental impact, and technological innovation. For every kilowatt of power generated, there is a need to think carefully about where waste will go, how it will be stored, and how it will be prevented from contaminating our ecosystems for millennia to come. This conversation is not merely an academic one. It has direct implications for energy security and resource allocation, which in turn shape the future of our technological landscape. Policymakers must assess nuclear energy's place within a diversified energy strategy, weighing its potential to support a sustainable future against the risks it poses. These decisions are deeply tied to the core of sustainable development. How can we meet the needs of today without compromising the ability of future generations to thrive? It's not just about finding new sources of energy, but about finding ways to do so responsibly. Indeed, when thinking about nuclear energy, it is crucial to consider its life cycle as a whole. From the hazardous mining process to the delicate and potentially dangerous task of decommissioning aging reactors, the need for rigorous safety standards and proper waste management is clear. A sustainable energy future cannot be built on the assumption that the challenges of atomic energy can be dealt with after the fact. We must address them now, alongside our efforts to harness atomic power. Governments and scientists must continue to grapple with the immense complexities of managing this energy source, trying to strike a balance between the urgency of energy demands and the need to protect the environment for future generations. As the world debates the merits and risks of nuclear power, it's essential that these conversations remain focused not just on the immediate benefits of atomic energy, but also on its long-term consequences. Only through such a balanced approach can we ensure that nuclear energy serves both the present and the future. At the same time, understanding the origins of atomic energy itself draws us into the realm of cosmology and quantum mechanics, where some of the universe's most profound mysteries reside. One theory that sparks both intrigue and confusion is the idea of quantum fluctuations. According to quantum mechanics, a perfect vacuum is never truly empty. Even in the absence of matter, it is filled with virtual particles that spontaneously appear and vanish due to fluctuations in energy. These brief, imperceptible shifts challenge our understanding of what constitutes empty space. During the infancy of the universe, shortly after the Big Bang, energy densities were extraordinarily high. Under these extreme conditions, quantum fluctuations could manifest as real particles, forming the building blocks of matter. As the universe expanded and cooled, these particles, quarks and electrons, could combine to form protons and neutrons, the fundamental components of atomic nuclei. This process laid the foundation for the formation of the first atoms. Another fascinating perspective comes from the theory of vacuum energy, which proposes that space itself holds an intrinsic energy. This energy may play a pivotal role in the creation of particles through a process known as pair production. where energy converts into a particle-antiparticle pair. This theory is compelling because it suggests that the universe's vacuum, often perceived as empty and void, is actually teeming with potential, ready to give birth to new matter when the conditions are right. Such discoveries have profound implications for both physics and our understanding of the cosmos. They challenge traditional notions of what empty space really is, and open up exciting avenues of scientific exploration. The concept of particles emerging from nothing pushes the boundaries of what we know about the fabric of reality itself. By probing deeper into the nature of quantum fluctuations, we not only uncover the fundamental principles that govern our universe, but we also get closer to understanding how the universe transitioned from an entirely energetic state to the complex and diverse matter we observe today. At the heart of quantum mechanics lies the uncertainty principle, which suggests that energy levels are not stable, but instead fluctuate in unpredictable ways. This principle plays a crucial role in our understanding of how particles and atoms can seemingly appear out of nowhere. These fluctuations occur on an almost imperceptible scale, too small to see, but their effects can be felt on a cosmic scale. The idea that energy can momentarily surge or dip, leading to the spontaneous creation of particle-antiparticle pairs, evokes a sense of awe and wonder about the very nature of reality. In essence, these fluctuations serve as a reminder that the universe is not static, but dynamic. At any given moment, the vacuum is brimming with potential, awaiting the right conditions for particles to emerge and evolve. This phenomenon reveals much about the unpredictable yet elegant nature of the universe, inviting us to rethink everything we thought we knew about space, time, and the origins of matter. It's this deep dive into quantum mechanics that offers a glimpse into how the universe itself may have been shaped, from its earliest moments to the complex system of galaxies, stars, and atoms we see today. The universe, in its most primal moments, was a place of immense potential, far from a static void. At the very heart of its earliest evolution, fleeting particles played a pivotal role. These transient entities weren't merely insignificant specks. They were crucial building blocks for more complex structures, like atoms, as conditions in the cosmos gradually shifted over time. During the formative years of the universe, these particles contributed to the creation of protons and neutrons, which in turn combined to form atomic nuclei. Their presence signified an energy-rich environment, one far from being empty, but instead teeming with the dynamic forces of creation. This dynamic flux hinted at an underlying universe full of untapped potential, a universe that would eventually give birth to the complexity we observe today. At the heart of this cosmic dance lies the theory of quantum fluctuations, which challenges the very fabric of reality itself. According to quantum theory, what we perceive as empty space is anything but. Instead, it is an arena where particles can spontaneously appear and disappear, as governed by the unpredictable nature of quantum mechanics. This universe, ruled by probabilities rather than certainties, raises profound questions about the very nature of existence. The implications of this understanding are far-reaching. They hint at a world much more intricate than we ever imagined, where even the vacuum of space is alive with possibility. These fluctuations are not simply random events, but rather indicators of a universe brimming with energy and potential, ready to evolve into something far more intricate and organized. As we move forward in our understanding, the concept of cosmic inflation becomes central. This phenomenon, occurring in the blink of an eye after the Big Bang, saw the universe expand exponentially, growing at an unfathomable rate. The field responsible for this dramatic expansion is known as the inflaton field, a scalar field hypothesized by physicists. It is believed that this field played an essential role in smoothing out density fluctuations, ensuring that the universe, while expanding, became more uniform. This rapid expansion not only shaped the cosmos, but laid the groundwork for the formation of the very building blocks of matter. In the moments after the Big Bang, the universe was an exceedingly hot and chaotic environment. But as the universe expanded, it began to cool, allowing the fundamental particles that had been in abundance to begin combining and forming more complex structures. Initially, only elementary particles existed. Quarks and leptons, the fundamental components of matter. As temperatures fell, however, these particles began to coalesce, forming protons and neutrons. It wasn't long before these protons and neutrons came together to form light atomic nuclei, a process known as Big Bang nucleosynthesis. This pivotal moment, occurring within the first few minutes of the universe's existence, was crucial for the creation of the first elements, hydrogen and helium, elements that would serve as the building blocks for all matter in the universe. The story of atomic formation doesn't end there. As the universe continued to age and cool, electrons began to combine with the protons and neutrons, leading to the creation of neutral atoms. This process, known as recombination, occurred roughly 380,000 years after the Big Bang and marked a significant milestone in the universe's evolution. At this point, the universe became transparent to radiation, allowing light to travel freely for the first time. The role of the inflaton field in this early universe cannot be overstated. Its influence helped determine not just the expansion rate of the universe, but also ensured that matter was appropriately distributed, creating the right conditions for the formation of the first atoms. At this stage, theories in physics began to shift in profound ways. One such idea, string theory, offers an entirely different perspective on the fundamental building blocks of the universe. Unlike the conventional view, which holds that particles are point-like entities, string theory proposes that the basic units of matter are instead one-dimensional strings. These strings vibrate at different frequencies, and their various vibrational states correspond to the different particles observed in nature. This shift in perspective has vast implications, not only for particle physics, but for the very nature of atomic structure. Within the framework of string theory, protons and neutrons are no longer merely collections of quarks. Instead, these quarks are also thought to be manifestations of vibrating strings. This idea suggests that the properties of particles, how they interact with each other, and how they combine to form atoms, are determined by their vibrational patterns. If string theory holds true, it could provide an entirely new way of understanding how atomic structures are built, opening the door to predicting the behavior of matter at a far deeper level. Moreover, string theory posits that the universe operates in more than just the familiar three dimensions of space and one of time. It suggests the existence of additional, hidden dimensions that could influence how particles combine and interact in ways we've never imagined. The implications of string theory are profound. If additional dimensions exist, they could offer new insights into how atoms bond and how the fundamental forces of nature operate. The very structure of matter, how particles interact and form the atoms that make up everything around us, may depend on these hidden dimensions. While string theory remains largely theoretical and unproven, its ideas challenge our most fundamental understanding of reality and provide tantalizing glimpses into the very fabric of the cosmos. Amid these cosmic revelations, the discovery of primordial atoms offers another significant insight into the early universe. These primordial atoms, believed to be the first elements formed in the aftermath of the Big Bang, include hydrogen and helium, two of the lightest and most abundant elements in the universe. The study of these primordial atoms provides a unique window into the early conditions of the universe, offering scientists a way to trace the evolution of the cosmos from its earliest moments. By understanding the properties of these atoms, we gain invaluable evidence supporting our current theories about the formation of the universe. This evidence not only reinforces the idea that the universe has been shaping and expanding for roughly 13.8 billion years, but also helps us understand the processes that led to the creation of the galaxies, stars, and all the matter that fills the cosmos. Primordial atoms played a critical role in the formation of stars and galaxies. Under the influence of gravity, these light elements coalesced, forming the first stars, massive furnaces where nuclear fusion began to take place. In the hearts of these stars, heavier elements were forged, transforming the early cosmic landscape and enriching the universe with the elements that would later become the building blocks for planets, life, and everything we see around us today. The creation of these stars and the elements they produced laid the groundwork for the universe as we know it, a universe rich with complexity, beauty, and life. Understanding the nature of primordial atoms is a crucial stepping stone in unraveling the cosmic narrative. It provides an essential foundation for delving into the life cycles of stars, the intricate forces that drive the expansion of the universe, and the complex dance of cosmic evolution. By tracing the origins of these ancient atoms, scientists gain access to a profound window through which we can examine the very structure and fabric of the cosmos itself. The study of primordial atoms is not merely a scientific pursuit. It is a journey that carries us through the vast expanses of time, tracing the evolution of the universe from its earliest moments. These primordial elements, formed in the aftermath of the Big Bang, are the building blocks upon which the entire universe is constructed. By analyzing their spectral signatures, unique patterns of light that are emitted or absorbed by atoms, scientists can unlock a wealth of information about the universe's age, its rate of expansion, and its fundamental composition. This analysis also extends to more elusive components of the cosmos, such as dark matter and dark energy, which remain some of the greatest mysteries in modern astrophysics. The implications of this research are profound, challenging and refining our existing models of the universe. As we explore the remnants of these ancient atoms, we open new avenues for inquiry into the mysteries surrounding cosmic inflation, the rapid expansion that occurred in the moments following the Big Bang, and the fundamental forces that govern the universe. The findings of this research continuously reshape our understanding of space, time, and the forces at play in the vast reaches of the cosmos. Yet the significance of studying primordial atoms reaches beyond the realm of science. It touches on deep philosophical questions about existence, purpose, and the very architecture of reality itself. As we trace the origins of the universe's building blocks, we are inevitably drawn to contemplate our own place within it. This pursuit of knowledge compels us to ask timeless questions. What is the nature of the universe? How did it come to be? And ultimately, what forces have led to the creation of the rich, diverse, and interconnected world that we experience today? As we venture into the heart of cosmic history, the study of primordial atoms becomes a way of looking beyond the surface of the universe to the very roots of its existence. It is a journey that enriches not only our scientific knowledge, but also our sense of wonder at the complexity and beauty of the cosmos. The more we learn, the more we realize just how much we have yet to understand, and how much there is still to explore. At the heart of this exploration lies the fundamental process by which atoms combine to form molecules. Through a mechanism known as chemical bonding, atoms join forces to create new entities with properties that differ significantly from those of the individual atoms themselves. Chemical bonding occurs when atoms share or transfer electrons, resulting in the formation of different types of bonds. Two primary types of chemical bonds are covalent and ionic. In covalent bonding, two or more nonmetal atoms share pairs of electrons. This sharing of electrons forms strong connections between the atoms, creating stable molecules. In contrast, ionic bonding involves the transfer of electrons from one atom to another. When this happens, the atoms become charged ions, one positively charged and the other negatively charged. These oppositely charged ions are then drawn to each other by the force of electrostatic attraction, forming ionic compounds. The nature of these bonds, whether covalent or ionic, has significant implications for chemical reactions. When molecules come into contact with one another, the bonds between their atoms can break, rearrange, and form new bonds. This process, known as a chemical reaction, is central to the creation of new substances. The properties of the resulting molecules depend on the types of atoms involved, as well as how they are connected. Take water, for example. Composed of 2 hydrogen atoms and 1 oxygen atom, it has properties that are vastly different from the individual hydrogen and oxygen atoms that make it up. Another key factor in chemical reactions is the energy involved. During a reaction, energy is either absorbed or released, which can affect how quickly the reaction occurs. This energy change is often facilitated by catalysts, substances that accelerate a chemical reaction without being consumed in the process. Understanding the rules governing atomic interactions and how molecules form is essential not only for chemistry, but also for the development of new materials, pharmaceuticals, and technologies that shape our world. Recognizing these principles also reveals the broader nature of chemical processes that govern life itself. Processes such as combustion, respiration, and photosynthesis, each of which relies on the interactions between atoms and molecules, play fundamental roles in sustaining life on Earth. The study of these interactions provides insights into the chemistry of life, offering a deeper appreciation for the delicate balance of forces that support our planet's ecosystems. Ultimately, the study of how atoms combine to form molecules opens doors to a deeper understanding of the universe itself. From the air we breathe to the stars in the sky, everything around us is made up of atoms and molecules interacting in complex ways. The journey of exploration takes us from the most microscopic particles to the largest structures in the universe, revealing the intricacies of a world that is far richer and more interconnected than we can immediately perceive. One of the most fundamental concepts in chemistry is electronegativity, the tendency of an atom to attract electrons in a chemical bond. This property significantly influences how atoms interact with one another, determining the nature of the bonds they form and the molecules they create. Atoms with high electronegativity, such as fluorine and oxygen, have a strong pull on electrons, leading to the formation of polar covalent bonds. In these bonds, electrons are unequally shared between atoms, creating regions of partial positive and negative charges within the molecule. The difference in electronegativity between two atoms plays a crucial role in determining the type of bond that will form. When the difference is large, one atom can transfer electrons completely to another, resulting in the formation of ions. This is what happens in ionic compounds like sodium chloride, where sodium donates an electron to chlorine. On the other hand, when the electronegativity difference is small, atoms tend to share electrons more equally, forming covalent bonds. This is seen in molecules like water, H2O, or carbon dioxide, CO2. Understanding electronegativity and the types of bonds it creates not only illuminates the behavior of molecules, but also provides insight into the chemical reactions that shape the world around us. Whether we are exploring the formation of stars, the chemistry of life, or the dynamics of the cosmos, the fundamental principles of atomic interaction are at the heart of it all. Through this lens, we begin to see the universe not as a distant, incomprehensible entity, but as an intricate, interconnected system in which every atom plays a vital role. Electronegativity is not just a fundamental property of atoms, it has profound implications for molecular geometry and reactivity. The way charge is distributed within a molecule significantly influences how it interacts with other molecules, ultimately determining essential physical properties such as boiling points, melting points, and solubility. For instance, water's remarkable ability to support life stems from the considerable electronegativity difference between hydrogen and oxygen. This polarity, with oxygen being more electronegative than hydrogen, imparts water with a variety of unusual and essential characteristics, such as its high surface tension, its capacity to dissolve many substances, and its relatively high boiling and freezing points compared to other molecules of similar size. These properties play a critical role in regulating temperature and facilitating the chemical reactions necessary for life. Moreover, electronegativity isn't just a theoretical concept. It provides invaluable insights into chemical bonding. By understanding the relative electronegativity of elements, scientists can predict how molecules will behave in chemical reactions, biological processes, and even industrial applications. For example, it helps in forecasting the outcome of reactions, the stability of compounds, and the formation of new materials in emerging technologies. In biological systems, this principle is especially crucial in understanding the behavior of biomolecules like proteins and nucleic acids, which are integral to life's processes. Electronegativity influences how these molecules interact with one another, aiding in processes ranging from DNA replication to enzyme catalysis. Catalysts are another vital concept in chemistry, playing a pivotal role in speeding up chemical reactions without being consumed in the process. At the atomic level, a catalyst provides an alternative reaction pathway that requires less energy to initiate, lowering the activation energy. This reduced energy barrier allows reactant molecules to collide more efficiently, increasing the likelihood of a successful interaction. A catalyst may temporarily bind to one or more reactants, forming transient bonds that distort the molecules into a more favorable position for the reaction to take place. By stabilizing the transition state, the high-energy intermediate arrangement of atoms, catalysts make reactions proceed more efficiently and quickly. One of the most well-known examples of catalysis occurs in biological systems, where enzymes serve as natural catalysts. Enzymes are crucial in facilitating biochemical reactions within living organisms by aligning substrates in the optimal orientation and reducing the energy required to trigger the reaction. Without enzymes, essential life processes such as digestion, energy production, and cellular repair would occur too slowly to sustain life. Catalysts, particularly enzymes, are also invaluable in industrial processes. They allow for more selective reactions, often steering the course of a reaction toward the production of a desired product. This ability to control reaction pathways is pivotal in industries ranging from pharmaceuticals to renewable energy generation, where efficiency and specificity are key. The role of catalysis extends far beyond the laboratory. It is central to the development of new materials, energy-efficient technologies, and sustainable production methods. In fields such as green chemistry and industrial manufacturing, catalysts are helping to create more environmentally friendly processes, reducing waste and energy consumption. In fact, catalysts are so important to the chemical industry that they are often regarded as the unsung heroes of many technological advancements. In recent years, the field of astrochemistry has uncovered a wealth of fascinating discoveries about the nature of molecules in space. Astronomers and chemists have identified a growing number of organic molecules in the vast reaches of interstellar space, challenging the long-held belief that the building blocks of life are rare. These discoveries are being made in dense molecular clouds where gas and dust accumulate, creating environments that are conducive to the formation of complex molecules. These clouds are the nurseries of stars and planetary systems, and they provide scientists with a glimpse into the molecular composition of distant galaxies. The presence of organic molecules in such remote locations suggests that the essential ingredients for life might be far more widespread than we once thought. Some of these molecules, such as amino acids and simple sugars, are the precursors to more complex compounds like proteins and nucleic acids, the building blocks of life. The ability of these molecules to form in the cold, high-pressure environments of space offers exciting possibilities for understanding the origins of life on Earth and the potential for life elsewhere in the universe. These findings are particularly intriguing because they suggest that the chemistry of life is not confined to our planet. If organic molecules can form in the cold, inhospitable expanse of space, it raises the possibility that similar processes could be occurring on other planets and moons, perhaps even in our own solar system. For instance, the icy moons of Jupiter and Saturn, such as Europa and Enceladus, are prime candidates for the existence of simple life forms as they contain the essential ingredients for life, including water, organic molecules, and the energy needed to fuel chemical reactions. As researchers continue to probe the chemical processes occurring in space, they are uncovering more about the fundamental forces that shape the universe at its most basic level. From the interactions of electrons in distant galaxies to the complex molecular machinery of life on Earth, electronegativity, catalysis, and the chemistry of space are all interconnected in the story of how molecules interact, evolve, and give rise to the diverse phenomena we observe in the world around us.